Hello, everyone. Good afternoon or good morning or good night, regardless of where you're located. Welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support that allowed this summer school happen. And I'm super happy to see you all here today, both on Zoom and on the parallel stream session on YouTube. I would like to note a couple technical and organizational details. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself or turn your camera on unless you have a question. We really ask you to put questions in the chat. That way it's going to be easier to handle the questions for the instructor and for the support team. But if you really want to speak up, of course, you can raise your hand and then we will let you unmute yourself and turn your camera on if you want and ask a question whenever there's going to be a good time in the lecture. I should also remind you all that this Zoom session is being recorded. If you're in a parallel YouTube stream session, you can leave your comments and questions in the live chat. We will try to handle them as fast as we can, either ourselves or we will direct the questions to the instructor and the teaching assistants. And thank you all for following these rules in advance. And we're continuing today's workshop day. This is our second workshop for today. And this afternoon session is with the experimental designs and experimental methodology workshop. And let me introduce you Dr. Libby Yankee, who is going to be our instructor today. She's an assistant professor of political science at the University of Houston and a member of political psychology research group at Stanford University. She's an experimental methodologist who uses methods including eye tracking and mouse tracking to obtain direct measures of decision processes, information accrual, and attention. And she studies questions of voter behavior, such as the role of identity in voter choice, gender and race's effect on candidates' evaluation, and variability in the voting models used by the citizens. Libby, the floor is yours. You can share your screen now, and thanks, everyone. And you're muted, Libby. Sorry.
Hi, sorry about that. So I'm Libby. Thank you everyone for coming today. I'm excited to talk about experimental methodology with you. Let's see. So before I share my screen, I just want to talk a little bit about my background and experiments, how I came to work in this area. So I got my PhD from Duke University a couple of years ago, and I was in a neuroscience lab for 4 years while I was getting my PhD. I wanted to look at basically if fMRI could tell us anything about voters and look into the methods that were in neuroscience and get sort of at a more micro level of individual behavior. Now, in this neuroscience lab, everybody used experiments, right? This was par for the course because neuroscience labs typically use fMRI or eye tracking. You can't simply go out and get observational data and use it. Instead, you have to bring people usually into an experimental lab that's in the university. And so the sample sizes don't tend to be that big. And so people always use experiments. So that's sort of how my training started off. But, you know, in political science, lots of people use observational studies. And so I sort of later came to really have to justify using experiments and sort of come to think of them as one method among many. So then last year, I published a paper with Jens Heinmuller, Dominic Hongartner, and Kurt Bansack using eye tracking. So that was a method that I picked up in the neuroscience lab. It was published in Political Analysis, and that was a conjoint experiment. So that sort of broadened my knowledge of experimental methods into this relatively new methodology of conjoint experiments that has entered political science in the past 10 years or so. Then last year, I ended up writing a special issue for Political Analysis on experiments. And so in that issue, I really delve into some recent advances that have been made and some recent, not recent, but some still long-standing questions and issues that experiments have in the political science literature. I guess where I am now is that I use experiments in most of my work, but I also use observational data. So Olga mentioned that I'm a member of a group at Stanford University. That group is run by John Krosnick, and his work typically uses observational data. And so all of my work with him, or not all of it, but part of my work with him uses observational data. And as you'll hear today, I do not think that experiments are the end all be all. And I'm going to talk a little bit about when you should use experiments and when maybe observational data is the way you should go instead for a project. Okay, so let me share my screen. And actually first, let me say today, I want you to ask questions whenever you have a question, okay? So as Olga said, if you write it in the chat, that's probably the quickest way for me to know that you have a question, but as soon as you have that question, please ask. So I will stop and ask if there are any questions a couple times throughout the lecture. But if you have a question on a slide when I haven't stopped to ask that, please type that in. I want to know that you are wondering about something, and questions that are just things that you don't understand that I have said are welcome. And actually, I'd be grateful if you ask those, because it probably means I have not been as clear as I should have been about something. And so I want to know that. So please feel free to ask questions whenever you have them. Okay. So let's get started. Okay. So you all should be able to see my screen now.
Yes, perfect.
Okay, great. Okay. So I'm going to start off asking for your participation. So there are 4 questions on the screen in front of you. And I want to just get you thinking, get your heads headed in the method space. What ways would you think about trying to go about answering these questions? So what type of data would you use? Maybe what method would you use? What sort of maybe regression would you run to answer the following questions? Okay, so why don't we start off with the first? Let's say we are wondering what the effect of intermittent fasting was on people's health, or people's lifespans, their chance of getting Alzheimer's or cancer. So I need a volunteer. So go ahead and raise your hand, please. And I'm sorry, I might mess up some of your names, but go ahead and correct me if I do. Baton, please go ahead. What, Baton, we cannot do.
Yes. Is this for the first question, as in the effect of intermittent fasting on health?
Yes.
Yes. So I feel that regarding the intermittent fasting, I think maybe for some people it has a positive effect, given some people do have certain amount of fat storage, and for other people it might be, not having a positive effect, given some people might be just weak. They don't really have sufficient amount of nutrients and everything in their daily lives.
Okay, so if you wanted to test this, how might you design a way to get data and to analyze that data?
Um, I would actually like, since these particular, like considering these people to be my patients, then I would just suggest a few group of people to follow a particular diet plan, which might be related to intermittent fasting. And the other group of people would be also given another set of diet plan, which wouldn't be intermittent fasting, but they would be thinking like it's a placebo sort of. So then I would see the effect on both and try to accumulate data based on that.
Okay, great. Thank you, Vatan. So you would basically run an experiment, right, to test
Yes,
this.
yes.
Would anybody argue for using observational data to answer this question? Go ahead, Joanna.
I suppose another way to test it would be through a longitudinal study that follows people who just like do intermittent fasting over the course of their lives, with a control group though, to see if there's a then discrepancy or a difference in their health or onset of Alzheimer's.
Okay, great. And Joanna, so which of these two would you choose to go for if you had to choose one method or the other, and why?
Well, the experiment can be conducted a lot quicker than a longitudinal study. So if it was only me doing this research and I needed a quick result, then the experiment would be the better way to go. But if this was in a research project or something that ran over a long course where I know that the means would be available to conduct this over several decades, then the longitudinal approach would probably be the better way to go.
Okay, so great. So practical concerns are always a reasonable thing to think about when you're doing research. So thanks. Let's move on to the second question. So the second
maybe?
question, yeah.
Sorry, in the chat, Annalisa also suggested that maybe partnering with a health app could be an option, or health insurance, for example.
Okay,
There
yeah.
option for that.
Yes. So more and more you're seeing people using the internet or apps to do research. And that's a really exciting method or methods that people have begun using. So thanks for that.
And there's also some questions on the chat. Aren't there ethical considerations pushing us to go towards more observational studies?
So yeah, so intermittent fasting, we aren't sure what the effects of that is on people, and there's an ethical argument to be made that people should get to determine for themselves how they eat. But on the other hand, I think that an IRB would allow you to get a group of subjects and assign some of them to intermittently fast and some of them not to. I don't think that would be an ethical violation. But yeah, ethics are definitely something that we need to take into account when we're planning to do any study.
And Bruce also have a questions about what about using historical observational data instead of collecting new ones?
Yes, so that's always an option, right? So for intermittent fasting, I would argue that probably experimental data is going to be better because there are a bunch of covariates that could also affect health, right? So there's how much people exercise, etc. And so because of those covariates and because of the possibility of multicollinearity, even if you include those in your regression analysis, I think that an experimental design would probably be best. But I also appreciate the arguments that Joanna made, and so there is not a right answer here.
Thank you. That's the question so far.
Okay, great. So let's move on to the second question. Are people's party identifications motivated by their issue positions, or do they choose issue positions according to their party identifications? So how would you go about answering this question? Go ahead, Victor.
Yeah. Hi. Yeah, I'd probably run a survey experiment. It's a bit tricky, but I'd probably run a survey experiment where part of the group is just asked about their party identification and their issue positions. But then part of the group, after noting their party identification, are given like a survey vignette, so a text which suggests basically that, which is fictional, which suggests that the party that they said they identify with has this and that. Those is like a narrative of what issue positions they have, and so, something fictional on that, suggesting that they have certain issue positions, and then asking them, the respondent, about their views on those issues, and seeing basically how big of an effect that appears to have. So how different are their responses on those issues to those of other respondents who identify with the same party but did not get the vignette. Something like that.
Okay, great. Thanks, Victor. Yeah, so this is sort of a hard question to answer because people's party identifications or their issue positions are hard to change, right? And like Victor said or noted, you would have to basically lie to your respondents or by giving them a fictional or a made up version of what their party has said in order to change their issue positions. Yeah. So this is a hard one. We're actually going to go over a paper that did something like this, but it used Donald Trump. And his issue positions during the campaign were all over the map. And so that provided an opportunity for an experimentalist to go in and provide people with something that Donald Trump had actually said, which was liberal, and provide other people with something that he had actually said on the same issue, but was a conservative stance. And so, but generally, this is a hard question to address through an experiment, simply because people's party identifications and their issue positions tend to be sort of difficult to move people on. Okay, any other ideas on this second question?
Thank you, Libby. There's an interesting discussion in the chat regarding these questions. So Hertie, for example, said that this is quite complicated, but he would run a minimal group study, for example. And Edward also thinks that there's an endogeneity, which is hard to get rid of under observational studies for this case. And Shuba asked the questions, isn't the directions of causality an important driver here?
So yes, so endogeneity, it definitely is an issue here. So that is saying that some people think that party identifications motivate people's issue positions. So in other words, people choose their party first. It could be because their friends or their parents belong to that party. And then because they are part of that party, they thus adopt the issue positions that that party has. The opposite causal arrow is also possible. The idea that people first form their issue positions, then they go look at which party best meets their issue positions on a broad array of issues or the most important issues to them. And so thus they choose their party identification based on their issue positions. And this is one of the reasons why you might want to use an experiment to answer this question, because we really aren't sure which way the causal arrows flow for this question. And that's something that experiments sort of uniquely get at very well. Okay. So let's now just move on to one more question. Let's look at the last one. So does Facebook cause people to get addicted to it? So can somebody sort of think about the theory that could be behind this and tell me, like, speaking of causality again, what is an example of one way that the causal flow could go with Facebook and addiction, and what is another example of how the causal flow could go regarding Facebook and addiction?
think this is a tricky one. We have no takers yet.
Okay. So I'm going to wait one more second. Go ahead, Christoph.
Yes, so there are, of course, a couple of possibilities. So one would be more from like a neuroscience perspective, that Facebook creates or releases some dopamine in people's brains, which causes them happiness, which then makes them to crave for more time on Facebook, which releases more dopamine, and so on and so on. Mm-hmm. So there could be a neuroscience explanation, but also maybe it's just designed in a way that makes it addictive. So like the mere design of reinforcing or like providing some kind of gratification for you to stay on Facebook. And the more you get gratified, the more you need the gratification, and the more gratification you get, the higher the level of gratification you need to experience the same happiness.
Okay, so sure, those are two different mechanisms, right, through which Facebook could cause people to get addicted. But you might also think the causal flow could flow the other way. So that is, people who are prone to addiction, and this could be many types of addiction. We could talk about Facebook or alcohol or drugs. So people who are just more likely to become addicted might look at Facebook more than people who aren't likely to become addicted, right? And so they might end up looking at Facebook really often, but it's not because Facebook caused them to get addicted. It's just that those people are inherently more likely to become addicted, to become addicted, and so they look at Facebook more than others do. Okay, and so this is an example again where you have this bidirectional potential causal flow. And so an experiment could really help you to get at this question. Okay. All right. Okay, so one example of experiments playing a very large role in a sort of public service announcement regarded smoking in the 50s and the 60s. So at around that time, there was a lot of data coming out that indicated that smoking cigarettes might cause lung cancer. Okay, so here we have a graph showing the death rate from lung cancer in England and Wales from 1900 to 1950. That's the blue line at the bottom there. And then the red line and the green line, which are dashed, are showing the consumption of tobacco in the UK and the consumption of tobacco as cigarettes in the UK. So you can see that all three of them are increasing over time. So these are correlated, and it suggests that there might be a causal relationship between lung cancer and smoking. In the 1950s, there were also some more micro-level results that indicated that smoking might cause lung cancer. So in 1956, one scientist by the name of Hilding confirmed that the cilia, which are hair-like structures on cells, were more likely to die among smokers where cancers were likely to develop. So that is in the lungs and in the throat. Auerbach was another scientist who in 1957 did some autopsy studies and found precancerous changes in the cells of smokers. So cellular pathology suggested that cigarettes might be linked to smoking, and observational data also suggested that. The cellular pathology was also observational data, but it was just at a more micro level. So the tobacco industry came up with actually quite a sophisticated methodological argument, I think, for a tobacco company. And their argument was that because there weren't any experiments proving that or showing that smoking led to lung cancer, these results were not strong results. So here we have a 1956 frank statement to cigarette smokers, which was released by the tobacco industry. And it said the following: distinguished authorities point out One, that medical research of recent years indicates many possible causes of lung cancer. Two, that there is no agreement among the authorities regarding what the cause is. Three, that there is no proof that cigarette smoking is one of its causes. And four, that statistics purporting to link cigarette smoking with the disease could be, etc., questioned by numerous scientists. So you'll see the word cause in here several times. So what they were saying was that observational studies just show correlation, they do not show causation. And so, there are many possible causes of lung cancer, and we can't specifically point to cigarettes as a cause of lung cancer. So that was despite the fact that in the 50s, the tobacco companies themselves had actually done experiments on animals. So this picture is from one of those experiments. And in those experiments, they had rabbits, which they separated into a control group and a treatment group. The treatment group smoked cigarettes, the control group did not. And then they looked at the incidence of cancers in the two groups. And they found that indeed, the treatment group, which smoked cigarettes, had more cancer than the control group. Now, they did not make these findings known because they thought that this would establish too much of a causal story around smoking and lung cancer. However, as we're going to talk about later, external validity is a reasonable question here. Can we indeed say that rabbits are the same as human beings, and so externalize the results in this study? We're going to talk about that a little bit later. Okay, so all of this led in the 1960s to the Surgeon General releasing a report on smoking. So this was a really big report. It went through all of the observational evidence that smoking led to lung cancer. However, this report also said the following: the causal significance of association is a matter of judgment. And in the 1966 survey, 60% of smokers agreed that the cancer link was not proved because it was only based on statistics. By statistics, what this survey means is observational data. So this is an example in which experiments weren't necessary, right? We all know now that smoking causes lung cancer. And that's despite the fact that we have not yet had an experiment on human beings proving, or coming closer to proving, that cigarettes actually cause that lung cancer. So we have had animal studies, which have now been reported on, but as I said before, the external validity of these studies could be questioned. However, the observational evidence is very clear that cigarette smoking does lead to lung cancer. And so let me start off by saying that experiments are not always absolutely necessary. Okay? However, they can be very helpful. So the following couple slides are correlations that exist that have likely no causal relation to one another. So here on the y-axis, we have the total US highway fatality rate. On the x-axis, we have the number of fresh lemons imported to the USA from Mexico. You can see that the two of them are correlated, but nobody would claim that these are causally related. Here we have autism and organic food sales throughout the years from 1997 to 2009. Again, they're correlated, but nobody would say that these are causally related. And then we have my favorite, which is the number of films that Nicolas Cage has appeared in and the number of people who have drowned by falling into a pool. Now, I don't know about you, but I've seen a number of Nicolas Cage films and none of them led me to suicidal tendencies. But maybe that's different for others. But again, people would not say that these were necessarily causally related, and yet some might because they're so highly correlated. And so experiments can really help us to get at this causality. Okay. So today we're going to go through why experiments actually work. So why can we say, or why do experiments give us a better idea of causal relationships? And we're going to look at that through the potential outcomes model. Then we're going to go, so that's actually the most math that we're going to do. And then we're going to go to experimental design and implementation. And this is where a lot of the work for experiments happens. So experiments tend to be pretty easy to analyze, particularly if you're just using the average treatment effect. That's just the difference in your dependent variable between your control group and your treatment group. So that's very easy to analyze. And so in experiments that use that type of analysis, most of your work is going to be done at the design phase. Okay, so we're going to talk about within and between subject designs, internal and external validity. And as part of that, we're going to talk about convenient samples like MTurk or university samples and how they compare to broader populations. We're also going to talk about confounders and randomization checks. So we're going to talk about balance tables and the idea of including covariates in your analysis of your experiment. Then we're going to talk about blocking. And then we're going to take a break and do some breakout rooms. I hope all of you got the email that I sent out earlier this week, or that Olga sent out, I believe, and came with an experimental design of some sort. Now, these don't need to be well developed. The idea is for you guys to take what we have just learned about experimental design and implementation and implement that in your own studies. So really think about, what is my current design? Is that within subject or is it between subject? And is that the right plan for my experiment? And finally, we're going to go over conjoint experiments, which, as I said before, is a relatively new method in political science. So we're going to talk about the theory of that and why conjoint experiments actually work. And then we're going to go through the implementation of a conjoint experiment using CoLab. Okay, so before we begin the potential outcomes, any questions?
There's nothing so far.
Okay. Let me also say, so there are a lot of you here, and you might be at different stages from one another. So some of you might be undergraduate students, some of you might be master's students or PhD students. There might even be a couple faculty members. And so for some of you, what we're going to cover, you may already know. And if that's the case for you, then I would encourage you to use this as an opportunity to think about how you would go about teaching this topic. So, I've chosen one method to do so, and you can see what you think about that method and how it works, and how you yourself would, if giving a lecture on a similar topic, go about doing it. So hopefully there'll be something for everyone in here. But I'm gonna assume that you don't know much about experiments and basically start at close to the beginning, and we'll move fairly quickly through it, but I am going to cover the basics as well. Okay, so what is an experiment? So we're going to talk about randomized experiments today. And randomized experiments are simply an experiment where you have a treatment and a control group, at least one treatment group, and usually a control group. You can also have two treatment groups without a control group, but typically you'll have one treatment and a control group, and where you assign your subjects into those units randomly. So you have a sample, and that sample is assigned randomly and an equal number to your treatment and your control. So randomized experiments can be done in a laboratory, so in person, or they can be done in the real world. So for example, I just read about an experiment that was done the other day. I think it was published in the APSR, where the experimenters, the experiment was done in German train stations. And what they did was they had an actor who was on the phone and who was also carrying a basket of fruit. Now, this actor dressed in a hijab, and then she accidentally spilled the basket of fruit while talking on the phone. In one of the treatment conditions, she was just speaking in a foreign language. And in another treatment condition, she was speaking in German, and and she was speaking about or in support of sort of traditional German values. And the outcome was whether people rushed to help her pick up the fruit that she had dropped or not. Okay, so that's an example of a real world experiment. You can also do online experiments. So you can embed a survey, embed an experiment in an online survey. And that has the benefit of A, usually being quite cheap, B, it being quite quickly, the time that you get your results back, and C, being able to reach a fairly broad set of people. So we're going to be talking about all three of these throughout the day today. But there are also other types of experiments. So one of these is a quasi-experiment, which is an experiment in which the people who are assigned to the treatment and control are not randomly assigned. So natural experiments or RD experiments, regression discontinuity experiments, are a good example of this. So for example, an RD experiment would be if you take somebody who has a certain threshold of blood pressure and you give those people a medication to help their health, then an RD experiment would be if you look at people whose blood pressure is just under that threshold and those whose blood pressure is at or just above that threshold, and you compare the two of them and their health, then you can see the effect of the medication. And the reason that this works is that it makes your sample be as if random between your treatment and control group. Okay, so quasi-experiments, RD experiments, the people are not randomly assigned to the treatment group because that treatment group was based instead on whether or not your blood pressure was above a certain threshold. Okay. So we aren't going to talk much about those today. We're going to stick to randomized experiments. So why do a randomization experiment? In order to get a better idea about causal effects. So it's often used in a situation in which there is unclear causality. So like we were talking about before with partisanship and policy positions, we aren't sure which one causes which. It could be that partisanship causes people to have their policy positions, or the causal direction could flow the other way. So an experiment allows you to get at this causally. So experiments are also very useful when you have lots of potential covariates. So for example, if you wanted to look at the effect of sleep on athletic performance. So there are lots of things that impact athletic performance. There's how much you practice, what you eat, how, your biology, how fast maybe you naturally are if you're looking at track events. And these covariates, you would say, well, you can just put all of those in a regression and control for them. However, there is collinearity between many of these. And so multicollinearity can really, really mess up your regressions. And so if there are lots of potential covariates that theoretically would impact a dependent variable, then an experiment can be helpful in sort of holding all of those things constant and just looking at the effect of a single covariate or variable on the dependent variable. However, you should also see Ratkovic and Tingley. They have a forthcoming paper, and that paper introduces a method to basically to isolate the effect of a single variable better in a regression from the covariates. And that can be done either on observational data or on experimental data. So that's just a slight something that you should look at if you are interested in that. Okay, and the third situation in which an experiment is very useful is when your independent variable that you're interested in can actually be manipulated. So if your theory involves a voter's sex, then it probably is not going to be possible to manipulate voter sexes in order to test that in an experiment. And so that would not be a case in which an experiment would be a good method to use. But on the other hand, if you're looking at, say, voters' attention to political news and the effect that that has on votes, well, you could assign one group to look at the news every day and assign another group to not look at the news at all, and then measure their votes. Okay, any questions so far?
Yes, nothing so far.
So I was going to ask you now to think about possible experiments, experimental designs that could answer one of these questions, but you guys already came up with a couple of them. So let's just move on. Okay, so why do experiments work? We're going to look at this through a potential outcomes framework. Okay, so let's say you have a 300-person sample. You have a treatment and a control, one treatment group and then a second treatment group. So each of these groups would have 150 people who are randomized from your 300-person sample into them. Let's say that your hypothesis is that people rate female candidates lower on likability scales because they are female. Okay, and your treatment 1 group is going to see a male candidate. Your treatment 2 group is going to see a female candidate, and these candidates are going to be exactly the same on all other candidate attributes. So their issue positions, where they're from, what they look like, their height, etc. So why does randomizing people into each of these 2 treatment groups tell us anything about causality? So why does this work? Whereas if we were just to take a sample of people from the world and ask them, is your senator female or male? And how much do you like them? Why couldn't we just do that? So to answer this question, I'm going to have to introduce some notation here. Okay, so stick with me. So we're going to assume that each unit or person in our sample, I, is exposed to a binary treatment. So either they're going to be in the control group or they're going to be in the treatment group. And we're going to have potential outcomes. Okay, so these are denoted yi1 and yi0. yi1 is the outcome for the group who received the treatment. yi0 is the outcome of the group that received the control. Then let's look at the individual level causal effect of a treatment. So that would be for a single individual, delta I. And what that means is you would subtract their outcome if they did not receive the treatment, if they're in the control group, from their outcome if they were to receive the treatment. Okay, so so that is delta I. It is the difference for an individual if they had received the treatment and if they had not received the treatment. But you might ask, people can only be in one of those categories. Either they receive the treatment or they receive the control. And I'll get into that in a second, so just hold tight. The last bit of notation that you need to understand is that our treatment variable is denoted by DI. So if DI is 1, then you're in the treatment group, and you're in the control group if DI equals 0. Okay, to put an example to this, to sort of bring these Greek letters into focus, say we're looking at intermittent fasting again. We're looking at the age of people's death, whether they intermittently fasted or did not intermittently fast. And we're looking at that conditional on their servings of meat per week. Okay, so the blue line at the top is people who did intermittently fast, and this is just hypothetical data. So that's looking at those who did intermittently fast, and you can see that as people eat more meat per week, if they intermittently fast, their age of death increases. Okay, so the orange line on the bottom is those who did not intermittently fast, and as they eat more meat per week, their age of death decreases. So eating meat is good if you're intermittently fasting, and it's bad for you if you are not intermittently fasting. So the expectation of yi given that di equals 1 is the same thing as saying yi1. So the expectation just means the average. So the average of our outcome variables, given that people were in the intermittently fasting group, so that would be the treatment group where d equals 1, is denoted by yi1. Okay, so that's the upper dashed line, which is just the average of people who intermittently fasted. yi0, on the other hand, is denoted as the expectation or the average of the outcome, so yi, given that di equals 0, or given that people were in the control group. So you can see again that that is the bottom dotted line, and that just denotes the average of people who did not intermittently fast. Now, delta here, delta I, is one person's difference between in their age of death between if they intermittently fasted and if they did not intermittently fast. Okay, so here we come to the main difference in between social science and the hard sciences. So in the hard sciences, it's possible to take, say, two cells and treat them exactly the same until you come to an experiment, put one in an experimental condition, one in the control group, and then you can conclude that any changes in the cells happen because of the experiment. However, with human beings, you can't do that. Now, this has been termed the fundamental reality of causal analysis by Holland in 1984, and that is that we only observe one of these outcomes. We only observe people's outcomes if they're in the control group or if they were in the treatment group. So yi or yi1 or yi0. Okay. So we term this the counterfactual outcomes for people to be the expectation of their outcome if they had been in the opposite group as they actually were in. Okay, so the counterfactual outcome for people who were in their control group would be if they were in the treatment group. So that's denoted EYI1, given that D equals 0. So given that people were in the control group, what would their outcome have been if they were in the treatment group? That's what EY1 of I given D of 0 denotes. So the counterfactual outcome for the treatment group, on the other hand, would be if this treatment group were in the control group instead, what would their outcome be? Okay, so those are termed counterfactual outcomes. And then we have our observed outcomes, right? Which for the control group would be their outcome given that they were in the control group. So yi0 given that D equals 0. Or for the treatment group, it would be their outcome given that they were in the treatment group, or the expectation of yi1 given that D equals 1. Okay. So I'm sure that everyone is with me. I want you to test your understanding. What do each of the following represent? So we have the expectation of yi1 given that d equals 0. Can somebody tell me what that represents? Baton, go ahead.
Counterfactual outcome?
Yes, the counterfactual outcome for who?
For the people who have been given the treatment, and it's the counterfactual outcome for the people who have been given the treatment if they were not given the treatment.
For people who were in the control group.
Yes, yes.
Yes, okay, exactly. So this indicates for the people who actually were in the control group, what would their outcome have been if they were given the treatment instead? Okay, so this is the counterfactual outcome for the control group. Okay, what about the next one? EYI0 given that D equals 0. Shubha, go ahead. Shubha, if you're talking, we can't hear you.
You can either unmute yourself and speak up, or you can leave your question in the chat if you want.
Okay, can I get somebody else to tell me what does the expectation of yi0 given that d equals 0 denote? Joris, go ahead.
That's the observed outcome for the control group.
Yes, exactly. So this is the outcome that we actually observe because yi0 is the outcome of the control group. Okay, so one more, just to be sure that everyone is with me. What does the expectation of yi0 given that d equals 1 denote? Natan, go ahead.
Yes, this is the counterfactual for those who has been assigned to the treatment group.
Yes, okay, great. So you all are with me. This is good. All right.
Maybe there is one question in the chat from Over.
Okay.
Is there a way to capture our uncertainty in the counterfactual group? Is it possible that there is a distribution of possible results of the same unit in the same group?
Well, this is just speaking hypothetically. And so this is theoretically, and so there wouldn't be a distribution that we would be able to capture. Okay. So why do we care about all of these counterfactuals? We care because hypothetical counterfactual outcomes are not, in theory, equivalent to the observed outcomes that we see in the real world. So let me give you an example of this. So this is using hypothetical data again. So let's say we have 8 people, and these 8 people actually had intermittently fasted or did not intermittently fast. So that's denoted here in the second column by a 1 or 0. And then we have their observed age of death. So if these letters are in red, those are people who did intermittently fast. And if they're in orange, then they're people who did not intermittently fast. So I want you all to get out your calculators, and I want you to compute the following. What is the mean of death or age of death, given that we observed people intermittently fasting? So among those who intermittently fasted, what was their mean age of death? And then subtract from that the mean age of death given that observed intermittent fasting equals 0, or given that they did not intermittently fast, what was their mean age of death? Okay, so go ahead and compute that. Okay.
We have some answers in the chat already.
Okay, let's hold off on that for just a second. Now, I would like to compute the following. So you'll see that the table has changed a bit. So now we have, as we did before, our observed age of death in the right-hand column here. But we also have people's counterfactual ages of death or their actual ages of death here. So for example, this person did intermittently fast and their observed age of death was 60. And so you'll see that their counterfactual sort of age of death, if they had been intermittently fasting, is also 60. But their counterfactual age of death, if they had not fasted, is 55. You can see for the second person who did not intermittently fast that that is the same thing as is in the second column, right? Which is the age of death if their intermittent fasting had equaled 0. So this is speaking in the hypothetical of this hypothetical. So we are just giving people an age of death if they had not fasted and an age of death if they had fasted, okay? So what I want you to do on this slide is go ahead and compute the mean age of death if intermittent fasting had equaled 1. So for that, you're just going to take the mean of this column and you're going to subtract from that the mean age of death given that intermittent fasting had equaled 0. So that's going to be this, the mean of this column here. So go ahead and compute that.
Libby, there is a question from Patrick could you explain again on how we can get the counterfactual?
Yes, so you'll see that some of these numbers are the same as the number that is over here. Okay, so we're assuming that this was their observed age of death. And so this person, for example, let's take the second person. Because they're in yellow, we know that that person did not actually intermittently fast. And so that is the same number as is in this second column. So that is their age of death if intermittent fasting had equaled 0. So if they had not intermittently fasted, this person would have died at 65. And we see that because this person did not intermittently fast, indeed, their observed age of death was 65. However, their age of death, if counterfactually they had intermittently fasted, would be 70. Okay, so that's sort of the opposite of this first person who did intermittently fast. So their observed age of death is the same as if they had intermittently fasted because they did intermittently fast. And the counterfactual for this person would have been if they had not intermittently fasted. So that would be over here and would be 55. So what we're doing is taking the mean age of death if intermittent fasting had equaled 1. So that's the mean of this third column here. And we're subtracting from it the average age of death if intermittent fasting had equaled 0, which is the mean of this second column here. Okay. So I'll give you just one more minute to go ahead and do that. Okay, so can somebody tell me what they found?
We have Bitan and Rusha in the chat that has results. Rusha, you want to maybe speak out? Yes, we have results in the chat. Do you want me to read it out, Libby?
Yeah, sure, go ahead.
Yes, Bitan has 7.5 and Rucher has 71.25.
Okay, so So 71.25 would have been the average age of death given that observed intermittent fasting was 1. It equally would have been the average age of death if intermittent fasting had equaled 0. But the answers that you should have gotten were negative 7.5 if we're looking at the observed data only, and 7.5 if we're looking at the observed minus and the counterfactual data. So in our second equation. So what I wanted you to see is that these numbers are different, right? One of them, the first one, says that the effect of intermittent fasting is negative, right? Whereas the second says that it's positive. And so whether you're using observed data or looking at your data through this counterfactual lens can make a large difference in your results. So in other words, observed outcomes in the real world are not necessarily the same thing as potential outcomes. And if that's the case, then observed outcomes can yield the opposite conclusion as the potential outcomes would have given us. Okay, so this is why we care about potential outcomes. So the case that we just looked at was a case in which the following was true. The expected outcome given that you were in the treatment group minus the expected outcome given that you were in the control group, that was not the same as the expected outcome given that you were in the treatment group minus the treatment group's counterfactual outcome. Okay, so but that is our goal. That is what we want to happen here, because the first part of the equation in blue is the difference between the treatment and control group outcomes, right? So we have yi1 given that d equals 1 minus yi0 given that d equals 0. That's just your control group average minus your treatment group average. And we want that to be equivalent to the difference between a group's actual outcome and the same group's counterfactual outcome, right? If you were to take, say, 2 cells that were exactly the same and put one in treatment and one in a control, this is the same sort of situation or the same logic just applied to people, right? So if you were to take somebody who had been in that control group and just hypothetically take them at the same moment with everything else in their life exactly the same and put them in the control group, what would their outcome look like? And that is the difference that we want to capture, because covariates are held constant in that case. And so any difference that you would see in your dependent variable, you would know would have come about because of the treatment. Okay, so we want that to be equal to the difference between our treatment and our control group outcomes. So how do experiments actually accomplish this? They do so because of the law of large numbers. Okay, so the law of large numbers says that as your sample size increases, the average of your sample on a variable is going to come very close to the average of the population from which your sample is taken. Okay, so yes, as n increases, the sample average basically equals the average of the population. Now, randomization means that you have 2 groups, or you end up with 2 groups that are drawn from the same population, right? And so what that means is that the average of your first group on a variable will equal the average of the population if your n is large enough. And the same thing goes for group B, right? The average of that randomized group B is going to be very close to the average of the population if your sample is large enough. And so what that means is that your average of A and your average of B are going to be the same if your sample is big enough, okay? So to put that back in the potential outcomes framework, what that means is that our actual outcome that we see for a treatment group should be equal to the counterfactual outcome that we see for our control group. And the opposite is also true. The actual outcome that we see for our control group should be equal to the counterfactual outcome that we see for our treatment group. Right? So if I were to put the former of these in the notation, that would be that the expectation of yi1 given that di equals 1 is equivalent to the expectation of yi1 given that di equals 0. Okay, so let me say this one more time. Why is this the case? It is because if our group is randomized and if our groups are large enough, then because of the law of large numbers, we can say that our outcome for a treatment group is the same as the outcome would be among our larger population. And we can say that the average of that variable among our larger population is also equal to the outcome for our control group. Okay, so the counterfactual outcome for our control group, right? So what this means, again, is that the actual outcome for one group is equal to the counterfactual outcome for the other group. Okay, let me stop for a second. Any questions so far?
Yes, we do have a couple questions. First is from Sergio. I know the data is made up, but are the counterfactuals calculated in any way or they were made in order to make the point?
Are you talking about this data here?
Yes, I think that's what it was referred to.
Yeah, no, they were chosen to make the point that the outcomes that you get for your average treatment effects here, so that is the intermittent fasting people minus those who did not intermittently fast, are different based on whether those are calculated just on the observed outcomes or on these hypothetical outcomes. Okay.
And we have another question from YouTube. How would you apply the potential outcomes approach for experiments with categorical outcomes that are not ordinal, or does it apply only to ordinal data?
So these also apply to categorical outcomes. I'm not going to go into exactly why they do right now. I'd rather finish up the example and sort of the logic. But yes, this applies to categorical outcomes also.
No more questions so far.
Okay, great. Okay, so what I just went over was that the law of large numbers tells us that the observed outcome for a treatment group is equal to the counterfactual outcome for our control group. Okay, so EYI1 given that DI equals 1 is equal to EYI1 given that DI equals 0. So now what we have down here below that is our average treatment effect, or ATE. And that is simply the difference in our expected outcomes. So this is the same thing as saying expectation of yi given that di equals 1 minus e of yi given that di equals 0. So in other words, these are our observed outcomes. So if di equals 1, what is our outcome? Minus what is our outcome when di equals 0. So that's this part right here of the equation. So on the right-hand side, we're just adding a little bit more detail and just saying that the outcome that we observe when di equals 1 is going to be yi1. And the outcome that we observe when di equals 0 is going to be yi0. So it's just adding this this 1 and this 0 here. Okay, so I think we can all agree that these are definitely equivalent. Okay, so you'll note that this term in yellow here is the same term that is in yellow up here. Okay, so what we can do is that because these two are equivalent according to the law of large numbers, we can simply take out the yellow and put in the green, right? So we have, instead of E of yi1, given that di equals 1, we put in E of yi1, given that di equals 0, okay? And that transfer causes us to end up with the following. So we have EYI1 given that DI equals 0 minus EYI0 given that DI equals 0. Now this right-hand portion of the equation is our counterfactual outcome minus our actual outcome. So what we end up with is that that outcome, our counterfactual outcome minus our actual outcome for a group, is equal to our experimental outcome, which is the left-hand side of that equation. So what we get when we apply the law of large numbers to the ATE is this result where our experimental outcome is equivalent to our counterfactual outcome minus our actual outcome. So that is that our experimental outcome is equal to if we had a single group and we're able to treat that group and treat that group as the control group, right? So this was our goal that I set in this slide here, right? To make the difference between our treatment and control group outcomes be the same as the difference between a group's actual outcome and their counterfactual outcome. So this is exactly what we ended up with. Okay, so let me just run through this again and give you a summary. So in an ideal world, what we would have is a single group, and we would be able to sort of simultaneously treat this group with our treatment and also treat this group as our control group, right? And we would look at the difference on the same individuals so that all of our other covariates were held constant. However, that is idealized because we can't actually do that in social science. Secondly, randomization, because of the law of large numbers, gives us the following. The expectation of a group's counterfactual is equivalent to a different group's actual outcome. Or in other words, the counterfactual outcome for the group that was treated is equivalent to the actual outcome for the control group. Okay, so that goes the opposite way as well. So the counterfactual outcome for the control group is equivalent to the actual outcome for the treated group. Okay, and if you simply write out the average treatment effect, so the difference between your control group and your treatment group's average outcomes, you can transfer in the latter half of the randomization equation for the former half of the randomization equation and end up with an equation where your experimental outcome is equivalent to your counterfactual outcome minus your actual outcome. Okay, so in other words, we get our idealized world from an experiment, okay, because the two are equivalent. Okay. So I want to be sure that everyone is with me. So these are sort of check your understanding questions. So the first one is, what would an ideal experiment look like if we lived in a hypothetical world where anything could happen? What would we choose to do if we could run an experiment in any fashion? Baton, go ahead.
So in a hypothetical world, I think that the established equation that we have, that the difference between the actual outcomes is equal to the difference between the counterfactual outcomes, that would be true, and there would be no contradictions to it.
So those would not necessarily equal each other, right, for an individual, because we're not saying that the actual outcomes and the counterfactual outcomes for an individual have to be equivalent. So can you try that again?
Yes. Um, so that would be for the population, I think.
Yes.
Yes. So for the entire population, the difference between the actual outcomes would be equal to the difference between the counterfactual outcomes.
Sure, sure. Okay, yes, that's a little bit more abstract than I was looking for, though. So can somebody else give me just like, if you were to run an experiment in an ideal world, what would it look like? And you would run this experiment on people. Savenya, go ahead.
We could observe both outcomes at the same person, like once when the person is treated and once the person is not treated.
Yes, exactly. Right. So you would have people and magically you would run an experiment on them at the same time. Basically, you would clone them. And one of them you would give your control and the other you would give your treatment to, because that would hold all other covariates exactly the same. So if there was a difference in the outcomes between those two versions of a person, you would be able to conclude that they were because of the experiment, because everything else would be exactly the same about them. Okay, great. So next question, what does the law of large numbers tell us? Someone besides Batan. No one knows? Nguyen, go ahead.
If I understood, can you hear me?
Yes.
So if I understood it correctly, the larger the sample, the closer your mean can be to the population, which means that it is as close as it is to the population that you're trying to study.
Yes, exactly, right? That was spot on. Okay, so if that's what the law of large number tells us, then what does that have to do with our counterfactual and our observed outcomes? So what does the law of large number tell us in terms of our counterfactual and observed outcomes? All right, Batan, do you know the answer to this one as well? Or is your hand just raised from before?
No, not really. Like.
Okay. Does anyone know?
So I have a private message from
Okay.
Bruce that the actual and counterfactual outcome should be identical.
Okay, so yes, they should be identical, right? And they should be identical between our two groups. So the counterfactual outcome for our control group should be equivalent to the observed outcome for our treatment group. And vice versa is also true. The counterfactual outcome for our treatment group should be equivalent to our actual outcome for our control group. Okay. And the reason that is the case is because both groups, the average, in one case it's hypothetical for the group, in the other case it's actualized. Both of those should be equivalent to the population mean, right? Because of the law of large numbers. Okay. So how does this lead us to believe that randomization yields causal inference? Or in other words, how does this lead us to believe that experiments actually tell us something about causes? Any ideas? Okay, so let's go back here and look at this last equation.
We actually have 2 responses in the chat. Sorry.
Okay, great. Go ahead.
So one is, well, several, responses. One is from Arathi. You'd assume that because the sample is large in both, I assume in both samples, and the randomization is true, the controls also get randomized, controls covariates. And then another from Tiago, because they give you the actual dimension of the treatment's impact, that's the causality or not existent causality is at play. And from Edward, the counterfactual can be recovered, circumvented, such that the fundamental problem of causal inference can be overcome.
Okay, yeah, so those were all saying what I'm about to say in slightly more abstract words, but those were all correct, okay? So if I were to put these in different words, what I would say is that here, the right-hand side of the equation, we can all agree on, right? So if we were to have somebody who was in the control group, and if we were to make a copy of that person and instead put that person in the treatment group, then we can all agree that any change in that person would be because of the experimental treatment, right? In other words, we would be sure that the experiment caused that outcome because everything else about that individual was exactly the same before they had had that treatment, okay? So in other words, the counterfactual outcomes for an individual minus the actual outcomes for that individual or for that group of people would definitely give us the causal effect, okay? And so by saying that the experimental outcome is equivalent to that counterfactual outcome minus the actual outcome, we are saying that the experimental outcomes also give us causation, or that we can read the results as being indicative of the treatment being the cause in that situation. Okay. All right. Any questions?
Nothing in the chats for now.
Okay. All right. So let's go ahead and take let's do an 8-minute break, and we'll come back at 11. And, oh, sorry, I forgot to say this. Sources on the potential outcomes framework and on experiments in that potential outcomes framework. You can look to the following texts for these. So there's Morgan and Winship, which is basically the book on counterfactuals and causal inference. It was written in 2007. Engrist and Pishka is a slightly easier, much shorter book that covers many of the main points. So it's called Mastering Metrics, and both of them are economists. And that was written in 2015. And then we have Rubin, and Rubin has many papers on this, but 2005 is one of them, and Pearl in his book Causality in 2000, and they're really the people who started the potential outcomes framework. And so sort of if you want to go to the root of where this started, I would look at Rubin and Pearl. Okay. So yes, now let's take a 7-minute break. We'll come back at 11 and we'll start on experimental design and implementation. Okay, so hi everyone, hopefully you're all back. If any of you are feeling sleepy, I highly recommend gummy bears as a sugar jolt. All right, so now we're going to move on to experimental design and implementation. So what that means is that the part of equations is done. So if you don't like math, then never fear, the worst is over. Okay, so we're going to start by talking about between and within subjects designs. So a between subject design is when you have your sample separated into the number of experimental conditions that you have. So in other words, if you have an experiment with a control group and 2 treatment groups, then you would separate your sample randomly into 3 different groups. So one group would just receive the control condition. Your first treatment group would just receive your first treatment, and the second treatment group would receive just the second treatment. So that's a between subject design. A within subject design, on the other hand, each of your subjects receives all 3 conditions. So they receive the control condition, the first treatment condition, and the second treatment condition. And what this means is that your dependent variable would have to be asked 3 times after each experimental condition. So you would give them the control, test your dependent variable, give them the first treatment, test your dependent variable again, and give them the second treatment, and again, test your dependent variable. So that is a within subject design. Now, when you want to use within versus between subject designs, I will get into in a little while, but first thing I want to cover is just the fact that your results can really depend on whether you choose to use a between or within subject design. So it's really important which one of these you choose. So several studies have found differences between and within subject designs. Nisi 2005 is one of these. So Nisi is an economist, and he found differences in magnitude based on whether he was doing the same experiment between subjects or within subjects. So for the experiment, people were subjected to receiving a low-cost lie or a high-cost lie from a car salesman. Okay, so the low-cost lie would only cost them a little bit of money. The high-cost lie would cost them a lot of money. And as the dependent variable, subjects were asked how unfair they found the lie to be. Okay, and specifically, the dependent variable was measuring the percentage of people who found the lie very unfair. Okay. So you can see that in the between subject design, those who were in the low cost lie group, 36% of them found that to be a very unfair lie. Whereas in the high cost group, or the high cost lie group, 62% of subjects found that to be a very unfair lie. Okay, so the difference was 24%.
Sorry,
yeah.
you're supposed to share your screen.
Oh,
you're not.
Yes, I am. Thank you. Okay. There we go. Thank you, Olga. Okay. So So yes, in this first between subjects design, as I said, the difference between the percentage of people who found it to be very unfair was 24%. Okay, so this is the upper row in the graph here. Okay, but in our within subject design, we found different numbers. So those in the low cost lie, only 18% of them found that lie to be very unfair. And a greater number of people found the high cost lie to be very unfair. So 68% of people found that to be a very unfair lie. So the difference was 50%, which is over over twice the difference that they found in the between subjects design. So in this example, the between subjects and within subjects design changed the magnitude of the effect. However, other studies have also found that you can get completely different results. So not just the magnitude of the effect changing, but the actual effect changing between and within subject designs. So Fox and Tversky in 1998 gave people two types of gambles. A clear odds gamble, where the odds of the gamble were very clear and people could choose to either take that gamble or not. And a vague odds gamble, where the odds were not made clear and people could choose to take that gamble or to not take that gamble. So in this case, the dependent variable was the percentage of people who chose to take the gamble. And when this was done in a between subjects design, that is that one group of subjects got the clear odds gamble and another group of subjects got the vague odds gamble, they found no ambiguity aversion in between them. In other words, the same percentage of subjects in both groups decided to take the gamble. Okay. However, when they did this in a within subjects design, so the same people were given the clear odds gamble and also given a vague odds gamble, in that case, people did show ambiguity aversion. Or in other words, fewer people decided to take the gamble with the vague odds compared to the number of people who decided to take the gamble with the clear odds. Okay, so in this case, the between and within subject design gave us completely different results. Now, one reason that this can happen is because of something called range effects, and it's also called context effects, carryover effects, or order effects. Okay, so when you're running a within subject design, it's really important to counterbalance your subjects. So what that means is that half of your subjects, in the example that I just gave, would receive the low cost lie first, and then would receive the high cost lie second. The other half of your subjects in your within design would receive the high cost lie first and the low cost lie second. Okay, so this is to account for the fact that the order in which subjects received the lies might have context effects, where people say might automatically rate the second option that they receive as more unfair than the first, or vice versa. So there are two types of carryover effects or order effects. The first type is symmetric order effects. Okay, symmetric order effects are when the difference between seeing a certain treatment first and second is the same as the difference between seeing the other treatment first and second. So let's put some numbers to this so you can see exactly what I mean. So in the first row of this table, we have the group who sees the low cost lie first and the high cost lie second. In the second row, we have the people, the group that sees the low cost second and the high cost first. So the order in which people are seeing the lies or being exposed to the lies is different between the first and the second rows. Okay. Then for our columns, we have the percentage of people who find the low cost lie very unfair, the percentage of people who find the high cost lie very unfair for the third column, and then the difference between those two columns for the fourth column, okay? So you can see that the numbers for 36 and 62 were the same as those, as the numbers for our between subjects design. In other words, when people see the low cost lie first, there's no context effects because it's the first thing that they see. And so we would expect the percentage to be about the same as those in the between subjects design. So that is this cell here and this cell here are the same as they were in the between subjects design. However, these numbers here and here are different. Okay, so let's say that if you saw the low cost lie second, 40% of people found that very unfair. Okay, and of the people who saw the high cost lie second, 66% of them found that high cost lie very unfair. Now, if you take the difference between people who saw the lie first and people who saw the lie second, you can see that that's -4 for both the low cost lie and the high cost lie. Why? Because 36 minus 40 is -4. So that's when people saw the low cost lie first and then second. And 62 minus 66 is -4. So that's people who saw the high cost lie first and then second. Okay, so these differences are the same here. Now, in the last row here, we have our counterbalanced mean. So what that is it's the mean of these two numbers here. So the mean the mean of subjects who found it very unfair when they saw the low cost lie first and when they saw it second. So the mean here is 38, the mean here is 64, and that's a difference of 26. So this cell right here is telling us the ATE, or the average treatment effect, right? Because it is the percentage of people who saw the high cost lie as very unfair minus the percentage of people who found the low cost lie as very unfair. So this is the difference that the lie makes, that the cost of the lie makes in the people who find it very unfair. Okay, so you can see that that ATE for the within subjects design is the same as the ATE for our between subjects design, okay? And to abstract just slightly, this will always be the case if the carryover or order effects are symmetric. In other words, if the carryover or order effects are the same for both treatments. So here we have mu1 and mu2, and those are the same as the between subject design averages because these are when the treatments are shown first. And then the means for when the treatments are shown second are mu1 and mu2 plus k, right? So we're adding the same amount to these two treatments when they're seen second. So that means that the difference here is -k. And if that's the case, then the counterbalance means are going to be mu1 plus k divided by 2 and mu2 plus k divided by 2. Okay, and if you take the difference between these two, that will be mu2 minus mu1, which is the same thing that we get in our between subject design. So what this means is that if your carryover effects between your counterbalance conditions in a within subject design are symmetric or the same for all of your treatment variables, then you are fine, okay? So in other words, in this case, the between subject design result is expected to be the same as your within subject result. And so you are, by saying that you're fine, what I mean is that you could do your design either between subject or within subject, and the results would be the same. However, now let's look at asymmetric carryover effects, okay? So as before, these two cells here are the same as the between subject design cells. Why? Because the person's seeing the low cost lie first, and so there is not any context effect in this cell. And in this cell, the person's seeing the high cost lie first. So again, there's no context effect. But let's say that when the person saw the high cost lie first and then saw the low cost lie, only 4% of people found the low cost lie to be very unfair. Okay, and this makes sense, right? So let's say somebody lies to you really badly and you ask them how unfair, and you say, well, that seems pretty unfair. And then they just lie to you a little bit. Well, compared to the first lie, it's not so bad. So I wouldn't call it very unfair, right? So this makes sense that fewer people would find the low cost lie very unfair when seeing it after they saw the high cost lie. On the other hand, the percentage of people who find the high cost lie very unfair when they see it second is greater than when they see it first. And this also makes sense, right? So if you were to see the low cost lie first, you might say, yeah, that seems unfair. And then if you were to see the high cost lie afterwards, you would say, well, I thought the first was unfair. I definitely think this high cost lie is unfair. And so a greater percentage of people might end up thinking that that's very unfair, okay? So the difference between the first and second time seeing the lie is different between the low cost lie and the high cost lie in this case, because these are asymmetric carryover or order effects. Okay, so the difference between 36 and 4 is 32, and the difference between 62 and 74 is -12. Okay, so when we compute the counterbalance means, you can see that the difference between those means, or the average treatment effect, or ATE, is 48, which is not equal to 26. Okay, so in this case, our between subject design did not give us the same effect as our within subject design did. And this generalizes, right? So to put some Greek letters to it really quickly, here we have mu1 for people who see treatment A first. People who see treatment A second, we're just adding K. So just assume that that is not equal to mu1. And then here we have mu2 as the mean for when people see B first. And then for when people see B second, the mean is mu2 plus R. So R, we're assuming, is not equal to K here. So we're allowing the difference between the people who see it first and people who see it second to be different between treatment A and treatment B. Okay, so the difference is -K and -R. The counterbalance means are, as you can see here. And so this ends with the ATE being mu2 plus R/2 minus mu1 minus K over 2. And unless R and K are equivalent, that is not going to equal mu2 minus mu1. Okay. So the take home here is that if your carryover effects are asymmetric, you have a problem. And you have a problem because this means that if you had run this experiment as a between subject design rather than a within subject design, your results would be different. Okay. And so what do you do if this is the case? Let's say you run your study, you didn't think that there would be carryover effects, but you actually do find asymmetric carryover effects. Well, a couple things. First of all, if your counterbalanced groups are large enough, then you can simply report your results as dependent on the order in which they were given. So for example, here I might say, okay, if we give the low cost lie first, this is our result. And if we give the low cost lie second, this is our result. And do the same with the high cost lie, okay? And this especially makes sense if you think in the real world that your treatment is typically or your two treatments are typically joined together, right? Because if, say, I were to do a between subjects design in that case, then my results from that study wouldn't actually be the results that I would find in the real world. If people usually saw, say, treatment A followed immediately by treatment B, and my results would not be the same because I would know from this within subject design that the results when treatment A is followed directly by treatment B are different from when treatment A precedes treatment B. Okay. So if you have enough people, you can go ahead and do that. If you don't have enough subjects, well, go ahead and get more subjects. Okay.
Libby, there is one question in the chat. Is it possible to show some respective examples of symmetric carryover effects and asymmetric ones?
Sure. Actually, let's go ahead and do this, and hopefully this will clarify it for the person. Okay. So would you need to be concerned if your data looks something like the following? Is this a symmetric carryover effect or an asymmetric carryover effect, and why? So why don't we go ahead and start by filling out this row of the table. So can somebody tell me what would the difference between seeing treatment A first and seeing treatment A second be? Get out your gummy bears, have them, and then answer the question.
There are some responses in the chat.
Okay, great. Can you please read them to me?
Yes, it's symmetric, 2, symmetric, 2. That's what people wrote, yeah.
Yes, exactly. Okay, so the difference here would be 2. Actually, let me just go here. Okay, so the difference between treatment A, if it's shown first and second, is 2. And you can see that the difference between treatment B, when it's shown first and second, is also 2. Okay, so this is an example of symmetric carryover effects. And why does this work? It works because when we then look at the counterbalanced mean, which would be the mean between 3 and 1, which is 2, and the mean between 3 and 5, which is 4, the difference between these two, or ATE, or average treatment effect, is also 2. And you can see that that's the same difference that you would find for your between subject design, which is 2. So you don't need to be concerned here. Okay. On the other hand, let's say this was 6. If this number here was 6 instead of 5, then the difference would not be equal, and that would be an example of an asymmetric carryover effect. Okay. All right. So any questions about this? Okay. All right. So
there is like a sorry, Libby, there is a question. Treatment B here can mean control, right?
Yes, it can be the control. And this also goes if you have more than 1 or 2 treatments. Okay, so that is that the carryover effects need to be equal throughout all treatments. Okay, so when you're choosing between a within subject design and a between subject design, it's really important to think about whether you will have asymmetric carryover effects or context effects. Okay, the benefit of between subject design being that there are no carryover effects because each of your treatment groups is only receiving 1 treatment or the control. Okay. So if you think that asymmetric carryover effects are theoretically likely, I would choose to do a between subject design rather than a within subject design. Another advantage of between subject designs is that it's easier to hide the purpose of your experiment from participants. So for example, in the experiment that we just looked at, subjects would likely know that you were comparing their reaction and how unfair they found a relatively low cost lie compared to a more high cost lie, right? And this is going to be more of an issue for sensitive subjects. So if you're studying racism or sexism, for example, a between subject design might be a better choice because the purpose is easier to keep hidden from your subjects. So as another example, let's say that you are looking at the difference between people's reactions to a female and a male candidate. And the candidates are the same on everything except for their sex. Well, if you were to do this in a within subject study, you would give them first either the male or the female candidate, and then second, the other candidate. And so because the candidate's sex is the only thing that changes, it would be quite obvious that you were looking at people's reaction to the candidate's sex. And because people know that sexism is generally looked down upon in society, they might actually change their answers in order to appear more socially acceptable than in fact they are. Okay, however, within subject designs also have some benefits. So first and foremost, they have increased statistical power compared to between subjects designs. So you need twice the number of subjects in a between subject design than you do in a within subject design. And so this is not such a big deal if you're doing an online study, which tend to be rather cheap and take no more time for you to get twice the number of respondents. But if you're running a laboratory experiment, this can be a real cost. So that's something else to consider. The last thing is that within subject designs, your covariates are held constant except for the timing that people receive the treatment. All covariates are held constant between your treatments and your controls. So in between subject designs, on the other hand, you have the possibility that your covariates are not going to be equal between your treatment groups. And so even if you randomize, your treatment and control group can differ on covariates, which means that they could confound your result. Or in other words, the difference that you find in your experiment could be due to this covariate rather than the variable that your treatment, or rather than your treatment condition, okay? And this isn't the case within subject designs, because in everything except for the timing of the treatment, all covariates are held constant between your control and your treatment. So those are some things to think about when you're choosing between versus within subject designs. Okay, any questions about within versus between subject designs?
Yes, sorry, we have one question. How should we check for the carryover order effect, a smaller scale pre-experiment based on literature?
Yeah, so I would say both are possibilities. So when you're planning out your experimental design, you should absolutely look at the previous literature to get an informed theory about what sort of carryover effects you can expect. So for example, in the example that I gave, if you just think about how people are likely to react, you would predict that the lies might impact each other. Seeing both of those lies would impact your response to the second lie. So that's one way to do it. And then the other way is to do a pretest, which I recommend always doing. And that's just to be sure that your experiment appears to work the way that you want it to, that your treatment actually affects the mechanism that you think it affects, and to check for these carryover effects as well. Okay, so I would do both.
Sorry, Libby, one more question in the chat. If we get the n large enough, does it mean that the problem of covariate not being equal would be alleviated due to the law of large numbers?
Yeah, so I'll get to that in a little while. The short answer is actually no. It doesn't mean that it will in all cases work. That randomization will always work. And I'll talk about how to deal with that in a little while. Okay. Okay. Now let's move on to internal versus external validity. So what are these? Internal validity simply refers to whether your experiment actually gives you or actually tells you the causal effect of A, your independent variable, on B, your dependent variable. And if you randomize effectively, then the assumption is that yes, any difference that you find from your experiment will be because of A, or your independent variable. That said, there are some more things to think about in internal validity, such as, can you actually define what your mechanism is? So many times, experiments will alter more than one aspect of their treatments between the treatment and the control group. So for example, if you're showing people different candidates, you might show them a picture of the candidate and also change the candidate's background or the candidate's issue positions. And so you wouldn't be sure which of those changes caused your result. So that's an issue that you need to pay attention to in internal validity. And we'll get into that more later. Okay, but internal validity is just, can you say that any changes in your experiment are because of the treatment? External validity, on the other hand, is a little bit more wide-ranging than people typically expect it to be. So external validity is not only asking, does your experiment say something about the real world? It's also asking, if you were to change your measurement variables, do you think you would find the same result? So if you were to ask your question this way instead of that way, do you think you would get the same result? The same thing with treatment variables. If you were to slightly alter your treatment, do you think you would get the same result? And then it also has to do with settings. Do you think that your result would hold across different settings and across different people? So those are all in reference to external validity. So this internal validity, or this idea that A causes B, how many different external circumstances do you think that will apply to? And by external circumstances, that can mean real world, but it can also mean just other experiments in which your measurement variables are different, or your treatment variables are different, or the population from which your sample is drawn is different. So, for example, let's go back to the beginning of this lecture, where we talked about the experiment with cigarettes and rabbits. So they found that smoking did increase cancer in the rabbits, but they only tested this on a certain breed of rabbits. All the rabbits were, I believe, the same age. So somebody could ask, well, do I think that this would hold if the rabbits are older, or if they start smoking at a younger age? And what do we think about, lop-eared bunnies versus some other type of rabbit? Would this hold for them as well? Secondly, the context. This was in the 1950s. I suppose one could argue that if you're in a very polluted area nowadays, that people are more likely to get lung cancer even if they don't smoke. And so maybe then the results wouldn't hold, where smoking leads to lung cancer because your control group would also have lung cancer. Or if you change the type of cigarette that they used in the experiment, this could also cause different results. So those are all external validity questions. So here's another example from a recent paper. So this is Barber and Pope 2019. And in this paper, the authors were trying to get at whether issue positions cause people's party identifications, or if people's party identifications causes them to adopt their issue positions. So this goes back to one of the questions that we looked at first today: which way does this causal arrow flow? And to do so, they used the fact that Trump expressed many different positions during his campaign. So what they did was they gave one group of their subjects a liberal position that Trump said on Russia and Vladimir Putin was one of the topics. And the other topic was free trade, so international free trade. So one group read a quote from Trump, which was identified as by Trump, saying that he supported a liberal position on these issues. Another treatment group was given a conservative Trump quote. So a quote from Trump expressing a conservative position on these issues. And then a third treatment group was given a conservative position by some other Republican in Congress, but just ignore that side of the graph here. So this is the part we want to pay attention to. So you can see that what they found was that when among the group that saw the liberal Trump position, Republicans were much more likely to say that they too supported the liberal position on that issue. So on the y-axis here, we have people's probability of voting for the liberal policy. That's voting for in quotes because they just simply said that they supported that policy rather than supporting the other policy. Okay, so when the Republicans saw the liberal Trump position, they supported that a lot more. On the other hand, when Trump took a conservative position, those Republicans also said that they supported the conservative position. So what these results imply is that people's party determines their issue positions, right? So, or at least Trump determines Republicans' issue positions, okay? So external validity questions. So what about a Democratic leader, right? Would the Democratic leader of the party, so Biden currently, have the same effect on Democrats as Trump did on Republicans? Would this hold for different issues? So if you were to try this with abortion or gay marriage, would it work? And you have to take into account issue salience too, right? So maybe this works on positions that aren't really central to people's ideology, but more central positions, maybe people are less likely to simply follow their party leader on because they have very firm positions on those issues. Would it work with different politicians? Would it work with different measures of issue support? So if they used a Likert scale, instead of simply asking, do you support this position that Donald Trump has given or not, would the results still hold? What if you included, I don't know, as an answer option? And the last one is, how long do these effects last, right? Because if we're going to assume that what these results mean is that people's issue positions are determined by their party, well, then you would expect that these might be really long-lasting effects. If they only last, say, a day or two, and then people go back to their previous positions, then the external validity of this study won't be as broad or as wide-ranging as it would be if these effects are actually long-lasting. So oftentimes you will face a trade-off that you have to make for internal versus external validity. So I'm working on a paper with John Krosnick right now in which we had this type of decision. So what we wanted to do was to look at whether the race and the sex of the vice presidential candidates made a difference in how people voted. So what we ended up doing was running an experiment 1 week before Biden chose Harris as his vice president. And what we did was we tested whether her race and sex impacted people's prospective voting behavior. So we gave people some information about all of the candidates. So we gave them first information about Trump and Pence, and then we gave them information about Biden and one of the following candidates. So Biden was considering a large number of candidates. So there were 6 Black females who he was considering, 5 white females who he was considering. And then we added in 1 Black male candidate, we chose Booker, and 1 white male candidate, we chose O'Rourke for that. So people read the information about Biden, and then they were given information about one of these candidates. So one person received one of the Black female candidates, one person or another person would have received one of the white female candidates, etc. Okay. So this was a unique time to do this experiment because it was the first time actually that a vice president has been a minority. So previously there was not any real world opportunity to test this. And we did not think that if we were to run this experiment with fake candidates, we would necessarily get very externally valid results. So in this example, we had real candidates. It was very timely, right? It was run right before Biden chose Harris. And so people had some general knowledge of these candidates. And it was in the middle of an election campaign where people were paying attention. So the external validity of this experiment was quite good, but the internal validity took a hit because since we were using real candidates, we had to change more than one aspect of the descriptions of the candidates. So in an ideal experiment, we would have only changed one thing about them. So here was one of the screens that people saw. So it says Susan Rice may be selected to run for vice president of the United States with Joe Biden this year. And you can see that it goes on to detail Susan Rice's previous jobs, what she did before her political career, her religious affiliation, and where she was born and raised. Now, because we used real candidates, all of these factors changed for each candidate, right? And their photo changed as well. And so what that means is that any difference that we found could be because of the fact that the candidate was Black, but it could also be because people liked her previous jobs, or because they liked her religious affiliation. So the internal validity in terms of really honing in on a mechanism was not ideal. Another aspect of our internal validity that wasn't ideal was that we had to measure prospective turnout, right? Because once Joe Biden had actually chosen a candidate, well, then I wouldn't expect, which candidates he thought about choosing to affect people's vote choice. And so this was an experiment that needed to be done when it was done. And we could only look at prospective turnout, and we couldn't actually find if these people had voted. So that's an example of some internal validity aspects that we chose to give up on in order to have greater external validity. And papers will often face this type of trade-off. Okay, so actually, let me stop. Are there any questions so far at this point?
No questions in the chat.
Okay, sorry, somebody else started speaking. Was there a question there? No, okay, all right. Okay, so external validity, the way that most people think about it is in terms of the sample that people have and whether those samples correspond to real world people. So if you're doing US politics, usually what you want to do is have your sample be the same as the US population. So I want to just go over really quickly the idea of probability samples and convenience samples. And then I'm going to review a little bit of the research on whether convenience samples are the same as their target populations. Okay, so probability sample is a sample for which the population members have a known non-zero random probability of being selected. So these can be online. So two places that are online but still have probability samples are TESS and Ipsos. And these are different than convenience samples, for which the target population members have an unknown probability of being selected into the group. In fact, these members are not selected into the group. Instead, they opt into the group themselves. So if you do a sample on MTurk, that is a sample of people who have chosen to be on MTurk. Same with Lucid, and same if you're doing a laboratory experiment on undergraduates. All of those undergraduates have chosen to be in your sample rather than you choosing them. The important thing is that your target sample and your population sample do not need to be the same on all covariates. Okay, what they need to be the same on is the variables that theoretically impact your dependent variable, or the covariates that moderate or mediate the relationship that you're looking at. Okay, so Druckmann and Cam 2011 looked at student samples at colleges and non-college samples. And they found that they were largely similar. Their partisanship was similar, their ideology, importance of religion to them, their belief in limited government, their views on homosexuality and immigrants, their social trust, their extent of both following and discussing politics, and general media use. All of those were similar. So to the extent that these variables impact your dependent variable, or the relationship that you are, not just your dependent variable, but the relationship that you are looking at, you should be fine using a student sample, even if it is a convenient sample. On the other hand, they found that student samples were different from non-college samples in terms of their religious attendance, their education level, of course, their age, political information, and on their racial attitudes. So if I was doing an experiment that was on racism, then I wouldn't necessarily be able to externally or externalize my results to the general population from a student sample. Researchers have also looked at the similarity of MTurk and other samples. So the CCES, which is a US-based, often used survey company. And they found that mTurk and the CCES sample had similar occupations and geographic locations. So that was Huff and Tingley in 2015. And the mTurk population has also been found to be somewhat similar to the US population. However, it has more women and fewer African Americans, more liberals, more young people, and more educated people, fewer married people, more low-income people and more unemployed, and more LGBT people. So if I was doing an experiment that I thought liberals would moderate, so in other words, let's say I'm looking at let's see, the extent to which a candidate talks about LGBT concerns and people's support for that candidate. Well, because mTurk has more liberals, I wouldn't expect the results of my experiment to generalize to the US population, and because it would not necessarily generalize to conservatives.
There is a question in the chat.
Yeah.
Patrick asks if we can say that the more homogeneous the sample, the higher the internal validity.
So that depends on your question, right? Because if I have a treatment that I don't think would be impacted by any covariates, then I wouldn't really need to worry about how heterogeneous my sample would be. But if, on the other hand, I have a relationship that I think would be moderated or mediated by many other variables, then the internal validity would be better if I had a more homogeneous sample. But the external validity would suffer. Okay. All right, any more questions? Okay. So now I'm going to talk about one aspect of internal validity, which is confounds. So internal validity, again, is the quality of your inference that any change that you saw happen during your experiment is indeed because of your treatment variable. So the idea is that A causes B. But confounds are other covariates that could have caused this relationship. And the question earlier is, doesn't randomization get rid of confounds because of the law of large numbers if your sample size is big enough? And so we don't have to worry about that, right? Well, ex ante, or in theory, randomization does balance covariates between your treatment group and your control group. That does not mean that it's always going to do so. Even if you have a very large sample size, you can simply get unlucky and have, say, more women in one group than you have in another group, or have a control group that has a higher level, average level of education than your treatment group does. So ex post, we might find that randomization has, quote unquote, failed. Now, it's impossible for randomization to fail if you have actually randomized, but randomization can fail to produce groups that are the same in terms of all of their averages on each covariate. Okay, so let's take an example. Okay, so let's say we have an 8-person experiment, and the blue squares are Democrats, the red squares are Republicans, and the squares that are outlined by green are our treatment group, and the squares that are not outlined are our control group. Okay, so let's say that I want to run an analysis of this data, and so I'm just going to run a basic model where Y, my outcome variable, is equal to alpha plus beta 1 times my treatment variable plus the error. Okay. So given that my data looks like it does, let's say that my treatment effect actually has no effect. Okay, so let's just say I know that my treatment effect should be 0. But I know that being a Democrat increases people's scores on the dependent variable. If this was the case, then what would the coefficient on my treatment variable look like in this regression, if that is my only variable that is in that equation? Anyone? So let me ask this a different way. So you can see that my treatment group is here in the green, okay? And my control group is down here. It's made up of mostly Republicans. And say that I randomized, but this is just the way that my control and treatment groups happen to be. This is just the way the dice fell, okay? Now let's say that I know that my treatment effect has 0 effect on the outcome variable, and that I know that Democrats have a positive effect on the outcome variable. If this is the case, and I just run the following regression, what should beta 1 be? Should it be positive, negative? Should it not be significant? What would I find?
There's an answer in the chat.
Okay.
Positive and significant, and another one greater than 0.
Yes, right? So this beta 1 should be positive. Why should it be positive? Even though we know that our treatment does not affect the dependent variable, nonetheless, because most of my treatment group is Democrats, thus this regression is going to pick up on the fact that the Democrats in my treatment group are higher on the outcome variable, and it's going to give me a positive beta 1, okay? Okay, so if both of my treatment effect and the effect of being a Democrat on my outcome variable are positive, what should beta 1 be?
Answers from the chat, still positive.
Yeah, it should be positive and greater than the coefficient would be in the first row, right? Because in this case, you would expect it to pick up on the positive effect of being a Democrat and the positive effect of the treatment, okay? So that would be a greater beta 1. What if the treatment effect was positive and the effect of being a Democrat was negative? What would beta 1 look like in that case?
Edward says that it depends on which force is greater.
Yes, exactly. It would depend on the magnitude. So if the magnitude of being a Democrat was, of the Democratic effect was huge, and the magnitude of the treatment effect was relatively small, then we would expect beta 1 to be negative, right? Okay, so, these 3 results would all indicate that likely the result of beta 1 doesn't actually match, in theory, what we said our treatment effect was, right? So when it has no effect, the effect of beta 1 is still, according to this regression, positive, okay? And when the treatment effect was positive, well, we find it has an even bigger positive effect than it actually has, Okay, so this would be equivalent to simply running the average treatment effect, right? We could have just found the average of the dependent variable among our treatment group, the average among the control group, and simply compared the two. Okay, I'm just doing it like this for a reason that you'll see in a second. Okay. Okay, so this is the reason that people recommend doing balance tests. What a balance test is testing that your covariates have the same mean between your control group and your treatment group. Okay, some people recommend doing balance tests on all your demographics. I don't recommend doing that because it's likely that by random chance, one of them will differ. And it won't matter that it differs necessarily, because all that matters is that the moderators and mediators, speaking theoretically, those covariates that theoretically should matter, those are the only covariates that you need to do a balance test on, okay? So, but in general, I'm a fan of doing balance tests to find out if you have a situation which is similar to this one, where, say, your treatment group just happens to be mostly Democrats and your control group just happens to be mostly Republicans, right? And it would be helpful to know if indeed that should impact your dependent variable. And so your result could be a result of the parties within your sample and your within your sample, your treatment and your control group, or it could be a result of your treatment and you don't know which of them is the case. Okay, so I'm on board with number one. Number two is that people tend to recommend including the covariates that differ according to the balance test in your regression as a covariate. So the idea is that they control for these different covariates, and whatever effect you find that is left over once that covariate is controlled for is indeed the true effect of your treatment. Okay, that's what people say. I disagree. And here's the reason. Okay, so let's put some numbers on this and say that these are the numbers that people had on our dependent variable. Okay, so in our treatment group, you can see that the Democrats were 10, 8, and 6 on our dependent variable, and our Republican, who was on our treatment group, happened to be 15. Okay, now this might strike you as an extreme outlier. But one of the most famous experiments in economics was on a Rand health experiment. And people found that actually an extreme outlier similar to this caused the effects of that experiment, even though it's really well known. Okay, so this actually happens in the real world. Okay, and then we have our control group made up of all Republicans, and they are 4, 6, 5, and 5. Okay, say that we were to run the following regression. Y equals alpha plus beta 1 times your treatment, so we have our treatment variable, plus beta 2 times Democrat, so we have a binary variable indicating whether people are Democrats or Republicans, plus our error. So this does exactly what some people recommend, right? So because we know that party IDs are imbalanced across our treatment and control groups, we include party as a variable. Okay? So let's say that we knew that our treatment variable had no effect, and being a Democrat had a positive and significant effect. If this was the case, what do you expect beta 1 and beta 2 to be?
From the chat, Baptist says the effect would be diluted between the two.
Diluted. So you expect positive effects of a small magnitude for beta 1 and beta 2. Okay. Any other guesses? Okay, so everybody's guess is that the positive effect that Democrats have on the dependent variable is going to be diluted and sort of spread amongst the treatment and the Democrat effect here, and that both of these betas are going to be small but positive. Okay.
Sergio has has
Okay.
another guess. He says 0 for beta 1.
Okay, so this would be the logic that underlies the recommendation that we include this covariate, right? So the idea would be that because being a Democrat soaks up all of that variance, that beta 1 would be correctly identified as having no effect on the dependent variable, whereas beta 2 would be positive and significant. Okay. So I put in the data that I gave here as the example, and I ran this regression. And the reason that there are more than 8 observations here is just that I copied these observations just so that there would be more of them in the data set. All right, and this is the result that came out. So beta 1 was positive and large, and beta 2 was negative and quite large, and both of them were significant. So even though Democrats were positive and significant in their effect, so you can see that the Democrats all have a higher score than the Republicans have. And even though the treatment is to have no effect, beta 1 came out as positive and highly significant. And why? It's because of this outlier here, okay? So this 15. And as I said, this has happened before in actual papers. All right, so let's take the second example. So say that both of them have a significant effect, okay? And that's positive. So being a Democrat increases people's level on this dependent variable, and also the treatment increases people's level on the dependent variable. However, yet again, we have this outlier, right? So except for this outlier, the treatment increases people's scores on the dependent variable. Any guesses as to what beta 1 and beta 2 should be here?
We have a guess, positive beta 1 and negative but small beta 2.
Okay, and whoever that was, can you tell me why you think that would be the case?
Vitan, if you could unmute yourself, if possible, or write in the chat and I'll read out loud. Thank you.
For the beta 1, I think it's going to be positive and significant because as we saw previously, the treatment is definitely having a positive and significant one. But in the previous one, we saw that despite the Democrats having quite a significant positive number here, they were still having a negative effect. So now if they both of them have a significant effect and the treatment is also doing its job, then definitely, although it's negative, it wouldn't be having that much amount of strength now.
Okay, all right, so that's a good guess. Any other guesses?
Baptiste has a guess on beta 2. He says it would be 0.
Okay, and Baptiste, can you would you mind speaking up and saying why?
I just thought that the outlier, the negative outlier would like offset the positive effect with the other.
Oh, sorry, I couldn't hear that. Can you try to speak up?
Sorry, I just said I thought the negative outlier would offset the positive effect from the other effects.
Okay, yeah, so that's a good guess too, right? So he said that the negative outlier would offset the positive effect that we see here. The positive effect of the Democrats, and that as a result, we wouldn't have any effect of being a Democrat on the dependent variable. Okay, so those are good guesses. So this is what we found. So beta 1 was negative and large and significant, and beta 2 was highly positive and significant. So it got the treatment effect incorrect. Okay. So for the third case, I again put in these numbers. So I said that the treatment effect was positive and significant, but the effect of being a Democrat was negative and significant. So I put in 0, 5, and 2 as the Democratic treatment effect, and 0 for the effect of being a Republican, but also being treated, right? So I figured that if we say that the treatment effect is positive and the effect of being a Democrat is negative, then maybe for this individual, they would end up at 0 on our dependent variable. And then 5, 4, 6, and 5 for the Republicans' numbers, okay? When I put these numbers in, I got the following result. Beta 1 was negative and significant, and beta 2 was positive and significant. So I found the exact opposite of the treatment effect and the Democrat effects that should have been there. Okay, so all of this is to show that even if we find imbalance in our treatment and control group, if we include the variable in the regression, the covariate that is unbalanced, this does not necessarily solve the problem. And worse, we don't know if it solved the problem, right? Because we don't know if let's say from this example, if beta 1 was negative, we wouldn't know what the treatment effect actually was. And so we would not know whether this was fixed by adding Democrat to this regression or not. Now, largely, the chance that this sort of regression will get the answer right depends on the variance of these independent variables the variance on the dependent variable conditional on these independent variables. Okay, so for example, let's say that Democrats had a positive and significant effect, but their variance was very small. So Democrats all were within 1 or 2 points of one another, and Republicans were all within 1 or 2 points of one another. Then the chance that you're going to get an extreme outlier is less so than it is if you have large variances among these groups on your dependent variable. So that's one thing you can check. If you have very small variances, then you have a larger chance of your regression turning out correctly if you include the covariates. However, that's not a guarantee. This is simply a problem that really cannot be solved. So in sum, you can find out whether your randomization worked, but that's it. Adding in covariates does not necessarily solve the problem, and you don't know if adding in the covariate has solved the problem or not. Additionally, having a large N is not going to solve the issue. You can always get large outliers, no matter how big your sample size is. The chances of this happening go down as N goes up, but there is still that chance of getting an outlier that's going to mess with your results. So my recommendation is that we should all report balance tables on variables that we think theoretically matter. Why should we all do that? Well, because if you have a strong theory that, say, party identification should make a difference in your dependent variable, well, we want to know then if the treatment group and the control group are balanced in terms of party identification, because we know that if they aren't, that it could be party identification that causes our change in our dependent variable rather than our treatment. And so it's important to know if there is balance on theoretically important variables. However, if there is not balance, I still think that a paper is valuable. Why? Because no paper is 100% immune to problems, okay? And so I think it's important to say if you have balance or not, but just because a paper is not balanced, it does not mean that it should not be published. And the only fix that we have to this is replication. Okay, so I'm a big fan of replication. That is both across methods and within methods. And I think that that political science really needs to embrace it more than it has thus far. Okay, so that might not sound very appealing to you, particularly if you want to get a bunch of papers in. You know, you can say, well, I reported a balance table and it turns out that all my covariates were not balanced. And, you know, I think it should be published anyways, maybe. But I do not think that others will think it should be published, and I don't think it will get in. So why should I report my balance table? Instead, what you can do is, if you have the foresight and the time to do so, you can block on these variables that are theoretically important at your design stage before you have actually collected any data. So what is blocking? So let's say that, oh, yes.
Before you go forward, we have two questions from the chat regarding the last slide. Edward asks if the reason why the large N doesn't solve the issue is just due to unluckiness.
Yeah.
Okay.
Yes, that was the question.
That's the question.
Yes, it is completely due to luck. So you can do everything right. You can randomize correctly and simply get unlucky.
Okay, thank you. And then Nathan asks if the problem applies only for imbalanced variables. He says that many experiments incorporate demographics as controls to increase precision. Do you suggest including demographics as controls in experiments?
No, I do not. And it's for the reason that I just lined out here. So if you were to put in a demographic, like a gender instead of party here, the same thing goes. So you could have multicollinearity, or you could have an outlier that simply makes it so that including those covariates is not going to necessarily give you the correct answer. So I am not against including them for precision's sake, but I do not think that they are a solution to the problem.
Okay, one other question from Edward. He says that it strikes him as that controlling covariates would be risky, would risk something of a distortion, which we have also in observational studies. Does the logic apply to observational settings too?
So in observational studies, there certainly can be multicollinearity. So yes, this problem does apply, but the problem is unique to experiments in the sense that randomization is supposed to fix this, but you can simply get unlucky on randomization and it will not fix it. But yes, multicollinearity absolutely is an issue in observational studies as well.
Thank you. That's all the questions.
Yeah. Any other questions before we move on to blocking? Okay. So let's go with an example experiment where in our first treatment group, we are showing people a candidate. And in the second treatment group, we're also showing them a candidate. And the difference is the sex of the candidate. So in treatment 1 group, he is male, and in treatment 2 group, she is female. Okay. Now let's say that we randomize our participants, and this is the result. So we have 5 males and 1 female in the first group, and we have 4 females and 2 males in the second group. In other words, we've gotten unlucky with our randomization because gender was, or sex was not equally randomized between our control and our treatment group, or our 2 treatment groups. Okay. So what we could do is that if we had thought of this before our experiment, let's say that we expect people's gender to impact how much they like the male candidate and how much they like the female candidate. If that's the case, then in this example, we would be screwed, right? Because the males would probably like the male candidate, the females would probably like the female candidate. And so we wouldn't find necessarily any difference between the candidate's likability based on their sex. But if we were to switch the 2 groups and show the group on the left the female candidate and show the group on the right the male candidate, well, let's just say, hypothetically speaking, that males don't like female candidates and that female candidates like male candidates the same as they like female candidates. If that's the case, then we would find an effect. And so the sex of the subjects is a confounder in our experiment. Okay, so in order to fix this, what we could do is before we run the experiment at all, we could block on respondent gender. Because we expect respondent gender to have a large impact on how people score on a dependent variable, we would separate the female and male respondents, and then we would randomly assign each of them to the conditions within their sex. So that is, we would end up with groups that looked like the following. We would have 3 males in both groups and 3 females in both groups. It would just be that the males and females were first separated, and then we randomized within each group to get our 2 treatment groups. So that is what blocking is. Okay, so any questions about blocking? It's a pretty simple concept, and it's quite easy to do. And you don't even need to say know how your participants score on the variable that you're going to block on very much in front in terms of time of your experiment. This would be easy to do on mTurk. You would just ask people first, say, what's your sex, male or female? Then you would have the males basically go to one randomization and have the females go to another randomization, and just be sure that you end up with equal numbers of people randomized into your 2 conditions within the 2 groups. Okay. So any questions about blocking?
Baptiste asks if this is like stratified sampling.
Oh, I actually don't remember what stratified sampling is. Baptiste, can you explain it really quickly?
Yes, sure. So I know that, for example, especially for like political polls, we do stratified
I'm sorry,
sampling where...
just a second. Can you speak up a little bit, please?
Okay.
Thanks.
Is this better? Is this better?
A little.
Yeah. Sorry, my mic is so bad. No, just like in political polls here, usually they do stratified sampling, so they stratify to make sure that their sample has the same proportion as in the general population on age, gender, etc., etc.
Yeah, so it's similar in that you would want to be sure that the number of males and females were equal between your 2 groups. So it's similar in that you are sort of setting the number of males and females that you're trying to get for both groups. Okay, so yes, it is similar to stratified sampling. Okay. Good question. Any other questions?
There's another one from Nathan. He asks you to repeat how to implement blocked randomization in mTurk, Qualtrics, etc. And does this work with multiple covariates?
Okay, so yes, it works with multiple covariates, but you need to be sure that you have done it correctly. So let's say, so for this example, I'm going to use a really small group of people. Let's say we have 8 people in our sample. Say 4, actually. Okay, so how this would work is that in Qualtrics, you would first ask people, are you male or female? And let's say that we wanted to have 2 males in our treatment group, 2 males in our control group, and the same thing with females. We want 2 females in our treatment group and 2 females in our control group. Okay, so what you would do is people would answer the question, are they male or female? And then among the males, you would randomly select people to go into the treatment group or the control group. And you could actually stop it after 4 males signed up. So you would just, any other males who signed up, you would just divert and say, okay, you know, thanks for being in the study, you're done. So of those 4 males, you would randomize them in equal proportion into your treatment group and your control group. So you've done it with 2 in each group. And you do the same with the females. So let's say you had 6 females who were taking your experiment. Well, you would choose 4 of them, the first 4 to come in, and then those extra 2, you would say, okay, thank you, you are finished with your experiment. And of those 4, you would randomize them into your treatment and control groups so that you end up with 2 females in your treatment group and 2 females in your control group. Okay. All right. Any other questions? Okay. So now we're going to do 15
Sorry
minutes.
to interrupt again. Edward asks, but how to work with multiple covariates?
Okay, so let's say, so we have gender as one of them. And then let's say we have education as another. Okay, so we want equal numbers of college graduates as people who did not finish college or had less education than that. Well, then you would have the males go into a separate group, and you would randomize the education among, sorry, not randomize, you would find out their education. And then you would have a group of males in your control group that had a less than college grade education. And then you would have males who had at least a college education, and you would have the same for females. So it would just be another level or another layer of breaking people out into the groups and then randomizing within those groups between your control conditions. So it would look like something like this. So, yeah. Okay, so let's see if you can all see this. So the first thing you would do is you would find out people's gender or sex. And then amongst the males, you would find out their education. And so we would have a group of males who were highly educated, a group of males who were less highly educated. And among these 2 groups, within each group, you would want to randomize that group into your control and your treatment. And you would do the same thing with the females. I just didn't take the time to draw this, okay? Is that clear? Okay, I hope that's clear. Okay, so now we're going to go into breakout rooms for 15 minutes. And hopefully there'll be a person in each breakout room who came with some sort of a plan for an experiment. And for each of these experiments, you can just talk about one person's if you want, or you can have multiple people share their experiments and talk about these questions all together. But I want you to think about the following aspects of your experiments. So is the design that you have between subjects or within subjects, and is that the best design? So do you see a potential for context or carryover effects? Or do you think that there'll be, it'll be very easy to guess the purpose of the experiment? If so, you might want to use a between subject experiment. Another question you might ask are, theoretically, are there any important variables that will confound the experiment if they are not effectively randomized, or if the randomization does not lead your two groups to have the same average on that variable? And if so, can you use a blocked design of some sort? A third question is, how is the external validity of the experiment? So what types of real world situations will it apply to? Which will it not? And lastly, is your planned data source likely to limit the external validity of your experiment? Okay, so we'll come back here at 12:45, and I'll be going around the groups just to see how it's going. Okay, so go ahead and break out into your groups.
Hi, Libby. The breakout rooms will close in 45 seconds.
Okay, great. Thank you.
I think everyone's back.
Okay. Okay, great. Were there any questions or disagreements that came out of your sessions about what would be the best thing for a person to do, or any questions that you found that you just weren't quite clear on? No questions?
Nothing so far.
Okay, all right, great. So let's move on then. We have about 45 minutes left. So this is the final push. Hang on, I'm going to share my screen. Okay. All right. Okay, so for this final section, what we're going to look at is conjoint experiments. So hopefully some of you have heard of these. As I said before, they've been around in political science for about 10 years. They're brought in by Jens Heinmüller in, oh gosh, I'm not sure what year that paper was, about 10 years ago. And previously they had been in the marketing literature for about 20 or 30 years. However, Jens put it in the framework of potential outcomes, which was really useful, and let political scientists know about it. And it's a great method. It's easy to analyze and quite easy to use and quite powerful. So I wanted to go over it. And hopefully at the end of this, you'll understand, one, why conjoint experiments work, and two, how to do the analysis in order if you run a conjoint experiment. Okay. So this is from a paper that was recently published in 2020, not in political science, but this paper was looking at what sort of advertisements or public service announcements would cause people to sit, stand, just stay apart from each other during COVID. So you can see on the left-hand side of the screen, that was the control condition. So you can see it says protect each other, stand 2 meters apart, sit apart, shop apart, and play apart. And then we have our first treatment. And this was what was shown to subjects in the treatment condition. So this was a between subjects design. And I'm not sure if you can read it, but let's say the upper right hand picture says, doesn't think he has it, but will infect her sister. She's a doctor. The lower left hand picture says it's fine. It's just a normal cold. And then in the red, it says, we'll pass the virus on to his granny. If he had stayed at home, she'd have been okay. So what this treatment is trying to get at is the interpersonal relationships that COVID could affect. So the idea is that you might be okay, but people that you know, your grandma, your sick dad, your friend who is asthmatic, it could affect one of them. Okay, so they're seeing whether this interpersonal treatment will cause people to say that they will distance themselves from others and wear a mask more than this control will. Okay? But what I want you to think about is what exactly is the treatment mechanism here? So you can see lots of differences between the control and the treatment group. Rather than using stick figures, you're using actual people and pictures of people. The treatment on the right talks about many people, right? Talks about somebody's grandmother, somebody with an undiagnosed heart condition. Which of those people, if they found an effect, which they did, was responsible for the effect? Is simply saying that your grandma could be affected enough to cause people to take more care, or was it actually the undiagnosed heart condition that did it? So people maybe think that that they aren't around elderly people very much, and so maybe they don't need to distance themselves, but then they realize that even people their own age could have undiagnosed heart conditions or asthma, and so thus they will stay away from others. So it's important to know exactly what the treatment mechanism is, because if we want to think in terms of external validity, we want to know what other sorts of public service announcements would create a similar effect and get people to distance themselves and to wear masks during COVID. So unless the only poster that you're going to show people is indeed the treatment, you would want to know which aspect of the poster was the actual cause, okay? And this is often the case in experiments where our treatment has more than one change made compared to the control. So for example, the paper that I'm working on with John Krosnick, which looks at the effect of the vice president's race and gender. As I said before, there are more than one potential causes of any difference that we find. It could be because of, say, Kamala Harris's past jobs that people like her better. So this is an internal validity issue. However, often we just have to do this, right? We have to include more than one treatment mechanism in our treatment because just including one is too limiting. Okay. So conjoint experiments allow us to do basically both at once. They allow us to vary more than one aspect of the treatment, but still identify aspect-specific changes in the dependent variable. Okay, so these are within subject, repeated measures designs. So typically people see more than one version of the conjoint experiment, and so it's within subject. So this is an example of a conjoint experiment. So this would be the screen that's shown somebody. We have candidate A and candidate B, and it shows 5 attributes of these candidates: their gender, occupation, their position on gun control, their political party, and their age. Now, what's important to note is that within each of these attributes, we have several values, and which value people get for each candidate is randomized. So this is the values and attributes that were used in my 2020 paper with Kurt Bansack, Jens Heidenmuller, and Dominic Hangartner. So for ages, we had 5 different values from 37 to 77, and each candidate that people saw received one of these values chosen randomly, okay? The same goes for all the other attributes. So the candidate's gender, their occupation, their position on gun control were all chosen randomly from these values. So if you think about this as a typical experiment, you might think, well, what do we usually do to compute effects in an experiment? Well, you find the average treatment effect, or the ATE, right? And to do that, you compare those who got the treatment with those who got another treatment, or you can compare your treatment and your control group, right? And to do that, you just need to know the means of the groups on a single variable. However, if you were to take a single variable from here, that would be looking at, say, candidates who are 37 versus candidates who are 45, right? But at the same time as ages are being randomly chosen, all of the other attributes are also being randomly chosen, okay? So to compute an ATE, you would have 6 million possible unique profiles. So that is 5 times 2 times 5. And this is the number of values that are within each attribute. So age, we have 5 values. Gender, we have 2 values. Race, we have 5 values. If you multiply all of those out, you have 6 million possible unique profiles. So the idea is that to compute an ATE, you would have to have at least 6 million people take this in order to, in order to be able to compute that, okay? So for our experiment, we had 30 profiles and 5, oh, sorry, not our experiment, but in just a hypothetical experiment, you would have 30 profiles seen by 500 respondents. That would be a total of 15,000 profiles. So the point is that you can't compute ATEs on a conjoint experiment because the possibility or the possible space for all of the different attributes, values are simply too numerous to do so. Instead, we compute average marginal component effects, okay? So as I said before, the ATE would be, say, a Republican versus a Democratic candidate, right? So to get that, you would compute the average probability that candidate A is chosen if he or she is a Republican candidate. And you would subtract from that the average probability that candidate A is chosen if he or she is a Democratic candidate, right? But we just went over why that's impossible to do in a conjoint experiment. Or not impossible, but very difficult to do. So the key, though, is that in a conjoint experiment, each attribute's values is randomly assigned, okay? And so we can think of those values the same as we think of pre-treatment covariates, okay? So if you remember back to the beginning of the lecture, we talked about the law of large numbers and how we can assume that that if our sample size is large enough, then the mean of our sample is the same mean as the population at large, okay, if we randomize. And so by randomly assigning each of the values to the attributes, we can similarly assume that the assignment of the values for each candidate is randomized. And so if we take a candidate who is Republican and a candidate who's Democratic over these repeated trials, the other values are going to end up being the same as they would be in a population, okay? So what this means is that for the AMCEs, all you need to do is calculate the differences in your dependent variable. So it might be which candidate you choose, or it can be how highly you rate each candidate between those different attribute values. So you could get together all of the candidates who are Republicans and compare them to the rest of the candidates who are Democratic, because you would assume that those candidates on the other attributes were on average the same. Okay, and you can assume that because, again, law of large numbers, we assume that both of those are equal to the assignment of those attributes in the population, and so they're equal to each other, okay? So what that means is that we can calculate the AMCEs basically the same way you would calculate ATEs, where you just need to look at the differences in means between those attributes on which one value was realized and the attributes on which another value was realized, okay? So the other way to run this is through linear regressions, okay? So the other attribute values in those linear regressions would be treated as dummy variables and would be tested against a certain value, which would serve as your baseline. Okay, so let's get into the design of conjoints, and we'll actually work on analyzing some real data together so that you can see exactly how this works, okay? Now, on conjoint design, typically people have 1 or 3 profiles on the same page. That's just what typically happens. In the marketing literature, I've seen as many as 5 on the same page, but I don't think any studies have looked at whether you can have more than 5 profiles. The number of attributes, on the other hand, studies have looked at. So if you have too few attributes, masking can happen. So an example of masking would be, let's say, somebody receives this as a conjoint trial. So you can see that there's only one issue position on here, the candidate's position on gun control. And masking would be if people inferred the candidate's other issue positions from their position on gun control. So candidate A, who strongly opposes gun control, I might think, well, that person's probably strongly conservative, and so is against abortion, is for religious schools, etc., etc. Now, masking is a problem because the effect that we find is associated only with the variable itself or the attribute itself. And so if gun control actually in people's minds is representing the candidate on a bunch of different issues, then the effect that we find for gun control would be probably much larger than the sole effect of gun control actually is. So you can also have too many attributes, and this can simply be difficult for people to look at. So for example, or an example is this screen here. So there are 11 attributes and 3 candidates. Now, in our paper, we looked at 5, 8, and 11 attribute trials. And we looked at 2 and 3 candidate profiles. So this was the most complex that the table got. And we found that people actually used bounded rationality in order to look at the attributes that they cared about the most, such that between the most complex table and a less complex table like this one, they actually overall we found the same AMCEs for the across the different levels of complexity. So people were just looking at whichever attributes were the most important to them. And so that tells us that up to 11 attributes with 3 candidates, you're probably going to get the same AMCEs because people just adjust their thinking process so that they can still look at whichever attributes are most important to them. So that means that you don't need to worry as long as your table is smaller or the same size as 11 attributes and 3 candidates. However, that also doesn't take into account that some candidates may be simpler in terms of topic than other topics are. And also that attributes can be different lengths. So they don't have to be one word like these are. They could be a sentence. And so that also needs to be taken into account. Okay, so you should also know that the probabilities of each value, attribute value being chosen can either be uniform or weighted. So for example, you could have all of these attribute values be equally likely to be chosen for a candidate. So you could say that it would be equally likely for a candidate to be white, Hispanic, Black, Asian American, or Native American. What we did, though, was to change this based on just facts about the likelihood of a real candidate having each of these attributes. So for age, for example, we made it less likely that people would get a candidate who was 37 or 77, and more likely that people would receive a candidate who was 45, 53, or 61. Okay, so this increases our external validity, and it does not decrease our internal validity at all. It just means that the results that we found are unique to this randomization distribution. So that's just an important thing to know when you're interpreting your results. Lastly, you should know that it's a good idea to randomize the order of the attributes. So for example, here this person sees political party, gender, then gun control. And you might want another person to see a different order of these attributes. So one thing that's typically done is to randomize the order across subject, but within the subject to keep the order the same in order to just avoid confusion. So that means that for a single subject, this ordering would stay the same throughout the different trials, but across subject, this order would change and would be determined randomly. Okay, so for interpreting the results, it's important to note that all of these are in reference to one value of each attribute. So let's start with the position on gun control. So you can see here that strongly support, so this is for candidates who strongly support gun control. You can see that that is at 0. So this is the reference point. So in comparison to a candidate who strongly supports gun control, we can see that people are less likely to choose a candidate who weakly supports gun control. They are even less likely to support a candidate who weakly opposes gun control, and even less likely to support a candidate who strongly opposes gun control. But all of these results here are in reference to this first candidate who strongly supports gun control. Okay. So as another example, we can look at prior political experience here. And the reference category is a candidate with no political experience. And we can see that compared to people's probability of choosing that candidate, people were more likely to choose a candidate who had been a mayor and less likely to choose a candidate who had been a governor, a US senator, or a US representative. The second thing to note is that these are average values. So what that means is that the distribution can vary. So for any one of these, you could have both positive and negative results. For example, on this weekly support, you could have people all the way down here at negative 0.05 and all the way up here at positive 0.25, okay? And this is the average effect across all subjects. You can also analyze your data such that the effects are conditional on a certain variable. So if you think that, say, Republicans and Democrats are likely to react differently to a candidate who strongly supports gun control, then you can look at the results conditional on party. Okay, we're not going to do that today, but that's definitely a possibility. So this is what the final results look like. So these are the AMCEs. So you can see the change in the probability of choosing the candidate, and all of them are have a reference value, and all of them are average values. Okay, so let's try it. Please go to Colab, and you can either use this link here, or I believe the link was given in the chat at the beginning of the session. Can we repost that, please?
Yes, it's posted in the chat.
Okay, all right, great. And is it easy to access? Yes, okay, great, thank you. Okay. So. Okay. Okay, so you all should see this on the screen in front of you if you're using Colab. So you can also run this in R. You should have received the data and the R script in an email. The R script is the same as this one. Are there any questions about finding Colab, or has everybody gotten that?
It seems that it's everything okay. No questions so far.
Okay, great. All right. So go ahead and start running it. So first, we're just going to load in some packages for Python. And then we're going to load in a package that allows you to run R in Colab. Okay. And then this should take 12 minutes. I tried it last night. And so hopefully everyone's computer will run at about the same on this. And go ahead and install those R packages. So while we're waiting for that to run, if anyone has any questions, either about what we've covered so far, or is having trouble with Colab, go ahead and ask them now.
There was one question that was asked in private message. So what is your usual setup for running your experiments? Do you use Colab or RStudio?
I actually use neither. I use Stata, but I also use MATLAB. And that is because of my work in eye tracking. So the lab that I was in, everybody used MATLAB because there's a program that you can write your experiments in that's really useful in MATLAB. So I use that. And then when I'm working with certain people who use R, I use R. So I'm all over the place in terms of which programs that I use.
Thank you. And also on, in addition to that questions, the person also asked, do you have any suggestions in terms of the hardware that is needed to run these experiments, or just the usual laptop is fine?
The usual laptop should be just fine in order to run this through Colab. Is that what the question was referring to?
Yes, I think so. I think they just want to ask on generally on running experiments, does it take a lot of computational power, or it should be okay with just normal usual laptop? Yeah.
Yeah, so in terms of running experiments online, even if you have like 5,000 people to take an experiment, a a normal laptop should be just fine. Okay, actually we don't have much time here. So I think what I'm gonna do is I'm gonna show you how to run this in R. So you'll just have to follow along. And then once this is done, then we'll go back to Colab and I'll just show you that it runs in Colab too, but I'm gonna use R and the same code in order to show you how this will run.
Libby, there is a question. How large of a sample size do we need for co-joins? I haven't seen a lot on power calculation for these experiments.
So it depends on how many trials you give people, right? So for example, in our 2020 paper, our 2021 paper, we used, I think, 143 people, something around that. But we had each person do 80 trials. And so our power was a lot greater because of that. If you have everybody doing only like 2 trials, then you're going to need more subjects. In general, I don't have like a specific number to give you. You can tell by looking at your 95% confidence intervals, right? If those are a decent size in terms of a decently small width, then you're fine. And if you don't have enough subjects, then those confidence intervals are going to be too large. But sorry, I don't have a specific number to give you, but I do know that somebody is writing a paper on it. I saw this about 6 months ago, and I can't remember who it was, but if you look up conjoints and sample size, I think that paper should come up.
Also, Edward would like to know about the problem of controlling covariates in an experiment. If you have any literature on this point, if you could recommend something.
So my favorite book is right here. It's Shadish, Cook, and Campbell. Experimental and quasi-experimental design for generalized causal inference. And it covers basically everything you need to know. So I would look in here. Okay, so so that we can finish on time, let's switch over to R. Okay. So, okay. So the first thing that I did, actually, let's just start from the beginning. Oops. Okay, so this is just installing the packages. So this package here was written by Kirk Banzak, and it is an effect plotter. So it plots the effects that come out of a conjoint experiment, and it makes it look very pretty. And that is available if you follow this link here. It is available there. So first thing that we need to do is go ahead and read in our data. So I'm going to do that. Okay. And then let's check out the data. Okay. So these are the first 50 rows of the data. You can see that we have here our subject identification. So all 50 rows are for a single subject. because we had many trials. These are the trial numbers, and you can see that they go from 1 to 17 in the first 50 rows. And you can see that we have more than one row per trial. That will become clear why that is in just a second. We gave people more than one block in our experiment. So this block, they were seeing 5 attributes and 3 candidates. In other blocks, they were seeing 8 attributes and 2 candidates, or 11 attributes and 3 candidates. So those were just differences in the conjoint tables that we were looking at, because we wanted to find if people acted the same regardless of the number of attributes and profiles that were included in the conjoint table. So this number of attributes and number of candidates, again, is just telling you the number of attributes and the number of candidates in that block. Okay, the preference here, this is our dependent variable. So you can see that in block 1, trial 1, for these first 3 rows, the person chose this 3rd candidate. So what the rows are representing are the candidates that were in a trial. So this first candidate, you can see their party value was 2. Their professional value was 2, military 1, gender 2, etc. This second candidate, party was 2, professional experience was 5, military was 1, etc. And then this third candidate, which was the candidate chosen by the person, their party was 3, the professional experience was 3, military 1, etc. Now, why are some of these NAs? That's because since in this block, they only saw 5 attributes, we randomized among those attributes to choose them. And so not everybody got every single attribute for every single block. So we randomly chose 5 attributes from our total list of 11. And for example, the race and the age of the candidate were not included in this block. So those are just NAs for these candidates. Okay. So that should give you an idea of what the data looks like. The next thing that we're going to do is, oops, we just need this one here. So this just tells it variable names, which we're going to use when we create our effect plots, okay? So here's the main part of the code here, all right? So we're creating a data frame here. And this row here for K in 1 to length of the attribute variable names. So what that means is that we have these 11 attributes here: age, party, race, professional experience, military, gender, etc. Right? And what this is saying is that for one of these variables at a time. Okay, so this K could be age or party or race. So that would be the K being 1, 2, or 3. Okay. Then we're going to subset the data by the trials that have that attribute. So if you remember how I said that certain trials did not include all of the attributes, we only want to look at the trials that did indeed include that attribute. So if you're just running a conjoint experiment that has a single type of table, so if everyone on every trial has the same number of attributes, then you don't need to worry about this part of the data. Okay? So next, we're going to read the regression as a formula, not a string. That's what this as formula paste is here. And what we're going to do is regress the preference that people had, so our dependent variable, on a single attribute at a time. So this is a key a key line of code that that you should have if you are running a conjoint experiment. Basically, you just need to run this as a regression. Next, this line of code just gets the estimate, the standard error, the t-value, and the p-value. So it's basically equivalent to this, but it just puts it in a different, like a different arrangement, okay? Then we're going to drop the intercept here, just because that's going to be our reference. And finally, we're going to put these results into a data frame. Okay. Next, we're going to set the column and row names, and then we're going to put them together into a data frame. So hang on, let me run this. Okay. So after this, you want to define the names of your attributes and the names of your values of your attributes. Okay, so this is for the effect plotter, which we are now going to run. Okay, so if we then go to wherever we told our PDF here to go. So this PDF here is telling you, it's telling R where your results should go to. And you can see that this is the result. Okay. So by now, your Colab should have downloaded all packages. Oh, hang on, let me. Okay. So all of your packages should be downloaded. So if you want to upload the file, all you need to do is go ahead and run that. And then you choose wherever you put the data that I sent you, called final data. Okay, you just want to open that. And it will load. Slowly it will load. Then you can go ahead and run this, and that should give you the output, the first 50 rows. So you can just make sure that that is the same. And then you want to get your list of variable names. Okay, so this would differ if depending on which attributes you decide to include in your conjoint experiment. And then you would need to make some changes to this code, right? So you would need to, for example, take this out if all of your trials had the same number of attributes in them. Then you would need to define your variables and or your attributes and levels of those attributes. And then you could look at what this gives you. So what this gives you is the estimate in the standard error and the p-value and the t-value for each of the values of the attribute. So this is in here, it's just identified as H2, H3, H4, H5. And if you think back to the value table that I showed you, this would be, I think, ages 42, 53, 67, and 77, right? And those would be in comparison to my base value, which was age 37, right? And these are the AMCEs, or your average marginal component effects. Okay. All right, so to get the actual PDF, you can't run it in Colab. So you would have to run this last bit of code in R for that to run. But you should be able to run up till here and find that you get the same effects as I'm getting. Okay, so are there any questions?
There
questions
are
for
no
now?
questions.
Okay, all right. So all right, so let's conclude here. So what we've gone over today is why experiments work at all in the potential outcomes frame. We've gone over several different aspects of experimental design and implementation. And we've also gone over conjoint experiments. So the sort of point that I want to leave you with is that I do not believe that experiments are the answer, the solo answer to all of our methodological problems, but they are an answer. So they are an answer because they allow us to get at causality better than observational studies do. However, they also need to be externally valid. So for example, take the prisoner's dilemma, right? This is a well-known experiment. So in it, you have two prisoners. They have the option to either confess or to remain silent. And both have an incentive or to confess, because if they confess and the other person remains silent, then they get out of jail free, right? So here we go. In this cell, person A would get out and person B would serve 20 years. Now, given that they both have that incentive, what are they both going to do? They are both going to confess, and they're both going to end up with 5 years. But if they had both simply remained silent instead, then they would both end up only serving 1 year. Okay, so hopefully you've heard of the prisoner's dilemma before. Let me ask you, what is a real world situation that the prisoner's dilemma applies to? Can you think of one? I have not been able to think of one, and the several people that I've asked have also not been able to think of one. Are there any thoughts about this? Anybody have a real world example of a situation that is the same as the prisoner's dilemma?
Theodore says trade negotiations.
Treat negotiations?
Trade negotiations.
Does he mean treaty negotiations?
No, I think trade like
commerce. Oh, trade. Sorry. Okay. So I'm sorry. Who did you say said that?
Theodore.
So Theodore, can you explain to me how a trade negotiation is the same thing as the prisoner's dilemma?
Well, you usually need to confess what exactly is your interest and what you're fighting for, or alternatively to keep it for yourself and exchange it for something else. So it seems quite similar. And I don't know, there are books that usually employ that technique.
Okay, so you're saying that if it is the case that if neither side were to say what they wanted in trade negotiations, then they would do better than if they both said what they wanted?
Not entirely sure about that.
Right, so this is a relatively small point I'm making, but thanks for that idea. But the point is that, you know, tons of time has been spent on the prisoner's dilemma as a way to measure cooperation. But I mean, it doesn't seem to have any external validity to me. And so I think that we should want to be careful that our experiments actually have some real world validity. Again, I talked about the different types of external validity, but if you can't think of one real world example of a situation that is similar to your experiment, then you might want to rethink your experiment. So just a quick note about natural experiments versus randomized experiments. So I gave before the example of a regression discontinuity design. So that's a natural experiment. So close selections are often used in RD designs. And one of the variables that people will look at is incumbency effects. Okay, and many of these studies have been done in the US, and the effect were exactly what you would expect. The incumbency effects were positive. So incumbents did better in elections than new candidates who are running. However, Klasny and Titunik in 2017 tested this in Brazil in the 1996 and 2012 elections, and they found that being an incumbent actually disadvantaged candidates. And so this is an example of the way in which regression discontinuity designs and natural experiments are really dependent on a specific time and a specific place. And so I would argue that generally the external validity of a randomized experiment can actually be as great as the external validity that you have in a natural experiment. So even though a natural experiment is done in the real world, and that's great, oftentimes they are very specific to a certain time, a certain culture, a certain political system, and they can't just be generalized. So natural experiments are oftentimes a great way to get data and to analyze data, but they are not a cure-all for the external validity problems that experiments face. Okay, so what I want to leave you with is that I think the answer is replication. And I mean that both within method and across method. So we need to replicate experiments that we think tell us important things about the world. In addition, we need to do observational studies on the same topic to show that these experiments have external validity. So why do we need replication of experiments? Well, because randomization does not always give us equality between the treatment and the control groups on covariates. And why do we need replication across different methods? Well, because every method has its downsides. Experiments have their weaknesses, observational studies have their weakness. And so I really think that replicating different studies is the way that the political science literature needs to go. Okay, well, that's it. Thank you very much for coming. We only went 5 minutes over, which I count as a success. Thanks to you, to those of you who participated today. That was great, and I really appreciate it. I hope I get to meet some of you in the future at conferences or other political science meetings.
Thank you, Libby. There's a lot of thank you in the chat as well from people, and a lot of appreciations from the participants.
Okay, and also if you have any questions or things that you disagreed with me about, please send me an email. I'd love to hear about it and talk about it with you some more.
There's some disagreement on the need the external validity, but I think that could be a discussion for another day.
Yeah. All right.